Okay, today we are going to start with lecture 4. Okay, let's have a quick recall of what we have done so far in this class. It has been a month, I think a little bit more than a month, but we have a long break. So roughly a month. What we have learned is basic linear algebra review, then we start to do modeling, right? Modeling, we have two parts. One is deriving system model from physical principles, your Newton's laws or circuit's laws or other kind of first principle model. And we also learn how to do state space model, right? And how to make continuous time to discrete time, how to have a continuous time state space model to transfer function model. Those are important things for the foundation for building up dynamical systems. Okay. So we also learned least squares, and also the reason we introduced least square is also because we want to use it to identify system model from data. Okay, it's part of the modeling process, data-driven modeling. But also least square itself is also very important, so we spend a little bit more time than we actually needed for control systems. Okay, I hope you get to know what least square is and how it can be used to do system identification. And now we have the system model. Okay, for dynamic system, now in your mind, it should be just a difference equation in state space form. Mathematical representation of the physical world. That's the state space model. And now we have a model. Our goal is to do what? Is design controller or analysis. Okay, it's analysis and the design. It's two parts, basically. Once you have a model, you can say something quantitatively about the system, whether the system have your desired behavior. You can start analyzing the behavior of the system. That's analysis. And then you can design controller to make your system behave in the way you want. Okay? So it's analysis and design, two parts. It's just like you formulate a system of linear equations. Okay? That's the modeling part. Right? And then in next step, you say, well, once I have the linear equation, okay, so the equality equation, what's the solvability, whether there exists a solution or not, things like that. That's analysis. And then you solve it. You develop solvers or you use a formula to solve the equation, similar to that. So in dynamic system, we obtain a model. Model is differential equation or difference equation. Now we can say something about the system. Okay, whether the system will behave in the way we want or not. If not, how do we design controller to solve it? So today, or the lecture 4, is more about this system analysis. Basically, we will introduce a few important concepts. One is called stability. Arguably, it's the most important concept in control. So stability. The next one is controllability and observability. Stability, I think most of you have heard of it. Maybe not formally defined, but you have heard of this definition or this term. But controllability and observability is not something you have learned before. That's the new stuff. Okay, those are related to it's like you have a equation. Let's say 叫什么方程 ？OK， 你要解方程 ？OK， 这个方程有没有解，能不能解 ？OK，the solvability of the controller design problem is about controllability, and the solvability of observer design problem is the observability. Okay, so all of these are built upon stability. So we will study these three, and before starting them, we have to know the system solution. We have to derive the system solution first. Okay. Before we analyze system behavior, we have to understand its solution. So that's how we start today. So let's consider we have linear system. In this class, modern control is mainly about linear system. I think I didn't mention this linear time varying and a linear time invariant system that much, but I think this terminology you somehow need to know. Okay, so if a system defines depend explicit on time. For example, if your system has the ABCD matrix depend on K, that's called linear, or just called time varying, okay? The system is time varying, it changes with time. If this ABCD matrix does not change with time, it's become time invariant. It's called, if it's linear, it's called LTI, okay? Linear time invariant system. Your system behavior, your system model change over time or not. Okay, so for example, if you have, let's say, if you have the spring damper system, okay, I think we gave an example during the modeling part, right? This is your control, this is the ground, let's say that. The system most likely is a linear, this is linear time invariant, doesn't change with time. Okay, it's linear time invariant if those spring constant, this is also K, but that's bad. Let's say if M does not change with time. Okay, but suppose the M somehow over time, every day it somehow gets reduced by 1 kilogram, then the system becomes time varying. Okay, at any given time, the M is different, then it becomes time varying. Okay, things like that. So we mainly focus on, our derivation works for most of the time varying case, but let's just say for notation convenience, let's say we mainly work on the linear time invariant. Okay, the system doesn't change over time. So for this kind of system, let's have derive its solution first. Okay, what do I mean by solution? If you simulate the system, you are solving it. You are trying to find its solution. In discrete time, it's very easy. You don't need to solve differential equation. You just need to derive recursive formula for the system trajectory. Let's work on this. I think all of you are good at these kind of calculations. For example, if you want to solve difference equation or differential equation, the very first thing you have to have is the initial state. Okay, you need to know where you start. What's the initial state? I'm given here is this x hat. Let's say if I have the initial state, then I can say my next time, what is the state trajectory at time 1? We're working on discrete time, okay? Based on this equation or state update equation, what I have is I just need to plug in the formula. I know x1 equal to a x0 plus b of u0. That's the law of your system. Okay? Next time it's just a x0 plus b u0, and because we assume our x0 is x hat something is given, okay? So it's a x hat plus b u0. Okay, that's the very first step. So if you know initial state, you know what's the input to your system, because input is something you decide. Okay, you know this. So you can compute what's the x1. Okay, and now you can compute, once you have x1, you can compute x2, isn't it? So what is the x2? x2 is a x1 plus b u1. Okay, but we want to know how it depends on the input history and the initial state. So I need to plug in this x1 expression. I will have a times x1. So a squared x hat plus ab u0 plus b of u1. Are you with me? Everything is a matrix vector multiplication, but it's I think everyone can get it very easily. So let's do one more, okay? Then we can summarize the rules or trend in the formula. So what about x3? x3 is a x2 plus b of u2. Okay, x2 is this expression, so I will have a times this. Okay, that will be a cubed x hat plus a squared b u0 plus a b u1 plus this one, b of u2. Okay. So from the expression, we can see some trend. Okay, this part is somehow depends on initial condition. Okay, I see. And this 3 term, and this 2 term, and this 1 term is keep increasing the number of terms. Those keep increasing number of terms depend on the input history. Okay, that's why it's dynamic system. It depends on all the past input. Okay, what you do today will impact who you are tomorrow and even 10 years. Okay, so in this way, let's see, we can summarize. So for arbitrary k, xk, can you guess the formula? What about this part? The things has a term that depends on initial state or initial condition. That will be a raised to power k times initial state. That's the first term. And then there's a somehow growing number term that depend on all the past history. If I just try to mimic this expression, I will say this will be a k minus 1 b u of 0, right? Plus a k minus 2 times b u of 1, all the way to a b u1. No, sorry. All the way to a b. This is the k minus 2 and the b u k minus 1. Okay, right? So because sk is a sk minus 1 plus b uk minus 1. Okay, so this is the last term. Okay, if we summarize it to it's a nicer formula, that will be a k x hat plus summation j from 0 to k minus 1. I'm just directly write down the answer. So this is k minus 1 minus j b of uj. J is a dummy variable. It's just something used to write down the summation index. Okay, if you plug in j equal to 0, you got the first one, right? J equal to 1, you got the second term. Eventually, you got all the terms. Okay, so if I have xk, yk is a static relation with xk. Basically, it's just a linear function of xk. So it's a c times xk, so a k x hat plus summation 0 to k minus 1. This is c a k minus 1 minus j b u of j. And of course, that's cx plus d of uk. Okay, so that's our output of the system. This, of course, this is the state trajectory of the system. This is state response, state trajectory. I would say this is the trajectory for a given input sequence. And this is the output, right? Output trajectory. Okay, it has 2 parts. I think you can recognize them. Of course, this one is the part depends on initial state. Okay, So this part has a term name called zero input response. If there's no input, that's the system response. Okay? And the second part, the whole thing, these two terms sum together, this is zero state response. If there's no initial condition, all the initial conditions are zero, then that's the system response purely due to input. Okay? So response consists of two parts. One is due to input, because you somehow excite the system or you are trying to stimulate the system response using external input. Another one is that if you don't give input, because the system has internal state, the state will correspond to some dynamic behavior as well. That will be the zero input response. Okay? I think you have learned this even maybe more in your circuit. 是吧？你们学电路里边没有 zero input response, zero state response 吗？啊？没听见，你说一下。控制支撑层里边有是吧 ？OK。If you know this is nothing but a convolution with the system input, okay? But anyway, for continuous time, you need to introduce a little bit more advanced stuff. But for discrete time, this is the expression. You already derived the differential equation formula, the solution for your state space model, okay? If you want to simulate, you just need to do a for loop and keep updating, keep iterating. You'll find the system trajectory. So discrete time, it's pretty simple to do simulations. Okay, we have the solution. I hope you can somehow remember, at least get familiar with the formula. Okay, I don't require to memorize anything because our test, you can bring this lecture note. You don't need to copy or remember formula, but you have to know roughly the format of it, so it's easy for you to work on solutions. Okay, that's the solution: zero input response and zero state response. Okay. Once we have the solution, we can start to think about analysis. Okay, let's first think about stability. Before that, let's clarify a few concepts, which is a regulation problem versus tracking problem. Regulation problem is, I'm not sure what's the official translation. It may be called 镇定问题. Most of the problems you encounter, maybe they can be posed as a regulation problem. And in contrast to regulation, there's a tracking problem. Okay? Your input reference keep changing, then you are trying to follow a changing reference that become tracking problem, 跟随问题, okay? 镇定问题. I think it's a large portion of control application can be transformed into regulation problem. Regulation problem, by definition, is keep certain function of the state or output close to a known constant reference value under disturbances of the system uncertainty. An example will be your famous example carpol. Okay? You just want this theta and the theta dot, it would be your state. Somehow you regulate that thing to be zero. You want everything to convert to zero. The theta part at least convert to zero. And also, if you want to take off your airplane, right? I mentioned that to you before. Okay. Then this is you may have a attack angle. And if you set a set point of the attack angle, my drawing is really bad. So then that's a regulation problem. Okay? It does not regulate to 0, but it's regulated to some known constant. Okay? But we always say we want to regulate the system state to 0 because the state often represents the error between your current position and also your desired position. Okay, you want the error to convert to 0. That's the regulation problem. For example, if you want to say I want a autonomous or cruise function, right? I want to, did you use the cruise function? It's maybe 70 or 100 kilometers per hour. If you drive that, you set the point, then they will automatically follow that speed set point. That's a regulation problem. Okay, a lot of things can be converted to regulation problem. Basically, want the system error to convert to 0. Okay, so or in the state space form, you want the state to convert to 0. You may ask, if it is not 0, of course, then you make the error to 0. Okay, so we only consider the error part. So 0 is somehow a representation of whatever you desire. Okay, the distance to your desired value. Okay, so but if something is keep changing over time, you want tracking. That's a different thing. Okay, it's you care the whole transient behavior. That's a tracking problem. We will talk about this later as well. But for now, let's focus on regulation problem. And the key for solving most of regulation problem is really understand the stability of your system behavior. Do you know what stability means? 云天，什么是 stability?
By definition, from control and engineering, output of the system will not diverge.
Will not diverge. The output of your control system will not diverge. You think that's somehow stable?
Yeah.
Anyone have a different opinion? Huh?
Yes, only.
Oh, you're talking about the BIBO, okay. Bounding, we are not talking about them in this lecture, okay. That's bounded input, bounded output, but you didn't say it right? Bounded input means bounded input lead to bounded output, okay. So that's BIBO stability. That's maybe what you have learned before. Okay, roughly speaking, whenever you say stability, I don't think we somehow introduce this for undergraduate students, but I want you to somehow know stability is often refers to or with respect to an equilibrium. For linear system, the equilibrium is just 0, okay? But for any other system, if you think about them, you want to generalize your concept of stability, it's often try to quantify your system behavior when it's away from its equilibrium. Okay, stability by default always means there's something you perturb the system and you want to return to equilibrium. Okay, what is equilibrium? I think I briefly mentioned that in the state space model, right? So for discrete time, let's say we work on discrete time now. For discrete time means equilibrium, let's not have u here, okay? So this is xk, that's next xk. So it should be xk. You stay there forever. Okay, in continuous time, x dot equal to fx equal to 0. You have to make sure the velocity at that particular location is 0. That's an equilibrium, but doesn't mean stable. So for example, I have this, suppose I have a ball, you think that will rolling back and forth, right? So where it will be an equilibrium point?
Either the point, either
this one, okay? The lowest tip will be the equilibrium. Because if I start from there, I will stay there. And if I don't have a velocity, okay, then I stay there forever. Right? That's equilibrium. It doesn't change anymore. If you just consider. This is the equilibrium. But if I have another upside down the thing, do you think this tip, is this an equilibrium?
Yes.
This is both of these points. So this point A, this point B for these two systems, these two different systems, okay? They are both equilibrium. Okay, so equilibrium definition, once you define equilibrium, then you know you can distinguish equilibrium. So one of them are stable, one of them are unstable. Which one is unstable? A is stable. B is unstable. Why? It looks stable? That's right. Okay, you have to have a mathematical. Well, I think many of you, if you see this figure, you can tell which one is stable or unstable. Okay, but that's your somehow intuition. But you need to formalize your intuition, use mathematical language. The language is that when you stay a little bit away from that equilibrium, can you return to that equilibrium? The ability to return to equilibrium, once you're not in that equilibrium, that's the stability. Okay? If I start perfectly at B, I will stay there forever. Okay, I will not change. But that doesn't mean it's stable. Stable means, okay, a little bit imperfect starting point. I'm a little bit off, then I'm totally off. Okay, I'll be further away from that equilibrium. I will never return. But the stable equilibrium is that no matter how far, no matter whether you're perfectly here or not, you will return to that eventually. Okay, so let me say a few more words. Suppose I have this guy like this. Okay, so how many equilibrium I have now? This guy, this is A1. Let's call this, now I call this A1, A2, A3. Okay, I have 3 equilibrium. 2 of them are stable. Okay, I'm still talking about roughly, but I already gave you somehow a formalism to say which one is stable or not. And, but then if I start from here, this A2, where am I going to converge to? I will stay at A2. Yeah, right? That's my equilibrium. Stay there forever. But I'm starting a little bit here. Let's say this is my Ix hat, initial state. Then somehow I'm pulling down to this first A1 equilibrium, eventually. Suppose I have some kind of friction, then eventually, if I don't have friction, I will just keep going back and forth, okay? So the system is not asymptotic stable, but it's still not unstable. It's just swing back and forth, okay? But if I start a little bit from here, A prime here, then this guy will just falling down here, right? I will convert to another point, which is A3, right? Depending on where I start, I will convert to different equilibrium. And so the region, the area, so this part will be the stability region of A1, and this part will be stability region of A3. So depending on where you start, you will convert to some equilibrium, okay? There's some equilibrium not global. Suppose I don't have this up and down, I just have one big valley, then everyone will convert to me. Okay, if I have some up and down, then depending on where I start, I will convert to different equilibrium. Okay, those things never happen in linear system. Okay, linear system only have one possible equilibrium. Okay, that's 0. So in this way, the reason I want to say it is that's the only way you can picture or think about equilibrium in the right sense. Okay, it's not about whether system is it's bounded or not. It's not about whether system diverge or not. It's really about your ability to return to equilibrium. Okay? So when I'm talking about the internal, I'm not saying BIBO is wrong. It's correct. Of course, it's another notion. But to truly understand control, you just need to make sure that you know, starting from non-equilibrium point, whether you can convert to equilibrium. That's the key for judging the system stability. Okay? That's why you have feedback, you have robustness. Okay, system a little bit off, you can still manage to do it. All right, because our model will often be wrong. If you say I have an aircraft, I designed the controller based on something, but I don't think you can perfectly say today everything is perfect. I know how many passengers, I know how much lunch they eat, so I know exactly the central math, I know everything, then I can control it. That's not true, right? So you have to be able to deal with uncertainty. That means if you're a little bit off, my control will make it convert to this particular point, okay? All right, so that's enough for general definition of stability. And this class, what I'm going to test you is not nonlinear because that's a complete another topic. Let's say, let's zoom into the system of linear system, okay? How do we understand the system behavior or internal stability? This is called internal stability, and the BIBO, bounded input, bounded output. Let's write it down. Bounded input, bounded output. I think that's what you have learned before. Bounded output stability. This is called external stability test, stability. Okay, for state space form that we are focusing on, that's we mainly care about internal stability. And in previous semesters, I also talk about BIBO, but now this semester I want to save more time for later, more advanced topics. So I will just skip BIBO. I think many of you have learned it. So, and what's more important is internal stability. Okay, when we study internal stability, we just assume there's no control. Okay, or you can think you have control but make it zero. That's also fine, but the truly means is what? It's really about, let me say it, it's mainly about autonomous system, autonomous system without control. Or, I don't think I spelled it right. Okay, autonomous. Autonomous. What's how to spell? N-O, okay. Okay, autonomous. Finally, I got it right. The example will be this. Okay. I can write down the state space form or equation for the system. I can ask whether the system is stable or not. Some equilibrium is stable or not. I can ask those questions. That's very important question for dynamic system behavior. Whether your system eventually converge or diverge, things like that. Okay. Or for control system, we want to know whether the closed loop or about the closed loop. The closed loop 闭环，可以吧 ？Closed loop system for which the control effect has already been considered. Okay, the controller has already. Oh, sorry. Already been incorporated. I think I mentioned the closed loop before. That's key, actually. So why we need stability? We want to make sure the closed loop system is stable. We want to design controller. After we plug in a controller format, the system is stable. For example, I can give you a quick example. Let's say example, I have x, let's say discrete time, okay? K plus 1 equal to 2xk plus uk. I can have a very simple example like this, okay? This is a control system. It's a little bit hard for me to think what stability means because stability is about equilibrium, right? But now the equilibrium depends on how I choose my control, all right? They depend on how I choose my control. So those notions are a little bit weird to define in exact form. But if I, let's say controller, the control law, let's suppose I have a control law. I have a P control, which is UK equal to -3xk. All right, I have a negative feedback P control, proportional control. That's fine. If I plug in this, then I have a xk plus 1 equal to what? -xk. Okay, this is a closed loop system because my control strategy has already been embedded. Are you with me? I plug in the control format. Control is nothing, a function of state, at least in this class, okay? So I plug in the control function, then control disappear because control completely being determined by state. So I have just a closed loop system. This is my open loop control system, right? Then I can say this system is stable or not. Because now I say, oh, if I design this controller, I find it out, it will convert to 0, okay? So the system will eventually convert to the state I want it to be, okay? So really, the internal stability is about state convert to 0, and it's really about autonomous system or closed loop system, okay? So starting this, we assume U is 0, okay? We just don't consider U in general, okay? Let's give this definition. The most important definition is internally stable or internally asymptotic stable, asymptotic stable， 渐进稳定，好吧？这听过没有？这常微分里头有这个是吧 ？OK， asymptotic stable means xk go to 0 as k go to infinity. Is that easy to understand? The state convert to 0. Again, 0 means something you want to be. Okay? If you say, I want to go to 2, not 0, of course, then make this your distance to 2 to 0. Okay? That's the change. So I hope you can find 0 is some reference point for you. And the key here is for all. I'm not sure whether you can find out the keyword here. Okay? Keyword, these are not important. This is important. For all initial state, then that's stability. It's not for one. Of course, if you start from 0, you're always 0. Okay? So for all initial state, it has the ability to converge, come back to 0, then they become stable or asymptotically stable. So for example, I can give an example. Suppose I have an initial state. Let's see, xk. Let me give a two-dimensional example because we're dealing with vectors most of the time. Maybe it's like half raised to power k initial state. And this is the third raised to power k x2 initial state. So in this case, xk, as k go to infinity, will convert to 0 for all x hat, right? No matter what x hat is, it always convert to 0. That's asymptotic stability. Okay? You can also find some case. For some x hat, it converts, but some don't. it will not be asymptotic stable by the definition, okay? And next one is marginal stable. We don't care that much about this, okay? It is class, but I want to define it. Marginal stable is just like what the Yuntian said, it's system not diverge. So the system remain bounded, but that's not convert to a particular point, okay? For example, I can give an example. Xk is sine 2 half pi k x2 hat, maybe x1 hat plus, I'm just making things up, okay? Half k x2 hat. Okay, you can see the second term converge to something, but not 0. Okay, and the first one keep oscillating. Okay, so for example, if this system, if there's no friction at all, it's not asymptotic stable. It's marginal stable. This guy is unstable. It just diverges. This guy, if there's no friction and just keep going back and forth, it is marginally stable. But for me, for us, let's call it not asymptotic stable, okay? It's just not stable by the standard. Okay, for this class, we mainly care about asymptotic stability, okay? Marginal stability is some kind of boundary case. We don't want to spend too much time to figure that out, okay? So asymptotic stability is the key. All right, are you with me? It's just whether the system starting from any initial state will converge to 0 or not. You may ask me, okay, what about initial state like this case? Sometimes convert this, sometimes convert that. How do we distinguish this? For a linear system, this doesn't happen. Okay, it's always just have one equilibrium, just 0. Okay, so you can either convert or not. So we don't need to worry about those cases for linear system. But for nonlinear system, that's a well-defined problem. So you have to consider so-called local stability. So locally, sufficiently close to the equilibrium, whether we can return. That will become the key. Okay. Now let's say we have recall state space solution for linear system that we just derived. This is what we have derived, right? For let's say for internal stability, let's not worry about this. Okay, for study for internal stability, we just let UK all equal to 0. Okay, we don't care about U for now. Okay, there may be no U, or it's already like a closed loop system. We only care this particular closed loop dynamics, right? That becomes very simple, right? Xk equal to a raised to the power k times initial state. Under what condition this converge to 0? So the stability becomes just studying a raised to the power k. Does that sound too simple to study? Becomes just linear algebra, right? As I mentioned before, modern control is nothing but exercises of linear algebra in the context of control design. Okay, let's see how we can use our linear algebra concept to study or obtain some conclusion. Let's start from the simplest case. Simplest matrix is, of course, all zeros, but that's trivial. Maybe diagonal, right? What about if I have a diagonal matrix? Then a raised to the power 2 is, can you do the multiplication? Then there's a lambda 1 squared, lambda 2 squared, lambda 3 squared. That's a raised to the power 2, right? If you have a raised to the power k, can you guess? Of course, you know what it is. So lambda 1 raised to the power k, lambda 2 raised to the power k, lambda 3 raised to the power k. Okay. For diagonal matrix, if you raise to the power k, this is diagonal raised to the power k by itself. So then for internal stability, I know u is 0. Okay, so I will say xk based on our formula a raised to the power k x hat. So the system is asymptotically, I will say asym. Okay? If and only if I say 2f, that's if and only if. Is that something you have seen before? Okay, if and only if sufficient and necessary condition 啊，充分必要条件，好吧？我们从高中、初中就开始学这玩意儿。If and only if what? In this case, lambda e, lambda 1, the norm less than 1. Okay? Lambda 2 less than 1, dot, dot, dot. Okay? All the way to lambda k. In this case, I have 3, right? So just lambda 3, let's say, less than 1. Right? i.e., all the, in this case, diagonals are eigenvalues, right? So all the eigens x lie inside unit circle. It could be complex number, by the way, right? Unit circle. Can eigenvalue be complex numbers? We didn't review too much about eigenvalue. I assume you remember them, okay? So all the eigenvalues lie inside unit circle. So eigenvalue, how many eigenvalues can be complex? If I have A in Rn by n, how many eigenvalues it has?
The greatest given and less than
It has n eigenvalues. Some of them may be the same, that's fine, right? But they have n eigenvalues. Of course. Because that's eigenvalue is the solution of lambda I minus a equal to 0, right? This is the nth order polynomial. Nth order polynomial have n roots. Some of them may be complex. That's it. That's Euler's PhD dissertation, right? So that's, I forgot whose, but anyway, so nth order polynomial has n roots. Some of them may be complex. That's why the eigenvalue is like that. Anyway, so we require all the eigenvalues. Some of them may be real, some may be complex. But if it's complex, they appear in pairs. Okay? It's conjugate of each other. So all of them have to lie in the unit circle in the complex plane. Otherwise, it will diverge because the norm will be bigger than 1. It will keep multiplying by itself. Okay? So let's take a break. We'll continue. Okay, let's continue. During class, I think a student asked me what does closed loop mean. I think I explained a couple times. Maybe it's better for me to draw the loop explicitly so that you know. So let me just use this example. Okay, do you understand what I talk? Why this is a closed loop? Where the loop is?
U equals to x times 3x.
Okay, let's draw the loop. Okay, so you know it's closed loop. So your system, the plant, in this case, is xk plus 1. We are in time domain, right? It's not frequency domain. It's xk plus uk. That's your system. That's an ABCD, that's a linear system. Okay? So it's a scalar case, so that's why it's easy to see. And the input to your system is your u, is always control, is the input. Output in this case, let's just call it x, right? this case. That's your plan. You want to design controller to make sure your output somehow behave in the way you want. Your controller, what does the controller do? Controller just need to decide control actions. The output of your controller is UK, right? The input of your controller, at least in state space form, it will be your state. Okay? At least there's a loop here, right? So your UK is nothing but -3xk. That's a proportional 比例控制器. Okay? Proportional control. If I plug in this, the system will converge to 0 eventually. If I plug in this, then the whole system behavior becomes the whole closed loop. If I think about this closed loop system dynamics, it becomes just this. Okay? In other words, if I plug in this, if I just substitute UK with -3xk, then I can combine these two blocks. It's different from the block diagram in frequency domain. You do that. Okay, everything is very simple in discrete time. In time domain, you just plug in this UK with this, you have the overall expression. Okay, so that's equivalent to say you have a system which is xk closed loop plus 1 equal to -xk. You just plug in it. Okay, so this is your closed loop system. That's why I call it closed loop system, that where the U disappears because you substitute the control law already inside it. Any questions? Okay, now let's continue our discussion on stability. We see the definition, we see the diagonal case. If the diagonal case, we see clearly that eigenvalues need to be less than 1, the norm, or the magnitude less than 1. What about the matrix is non-diagonal, is not diagonal? We can try to make it diagonal, right? So there's a class of systems that are called diagonalizable. Suppose this is all square matrix. This is all square matrix. 所有的方的矩阵, okay? Diagonal is very, very small, right? This is diagonal matrix. Very, very small portion of all matrix. But there is also a fairly large class of system which is not diagonal, but diagonalizable. But unfortunately, this class is not all square matrix. So there's some matrix is not diagonalizable. I'm not sure whether you know it or not. But doesn't matter. Let's work on this one first. Diagonalizable. If the diagonalizable, then it's almost the same as diagonal, because you can diagonalize it. It's almost like a change of coordinate. If in one coordinate system is coupled, in other coordinate become diagonal. Okay, so let's work on this case. Diagonalizable means A is diagonalizable. That means it's similar to a diagonal matrix. So it's T times D times inverse, T inverse. That's a similarity transformation. That's which is just a change of coordinate. Okay, D is diagonal. D is diagonal. Okay. And D, let's say D is lambda 1, lambda 2, lambda, let's call it lambda 3, or let's just use 3, that's fine. I think you know the general case. So D is the previous A, okay? Now, in this case, A raised to the power k is what? It's T d T inverse, T d T inverse, multiply k times. Okay? All the way to T d T inverse. But you can see those middle guys got cancelled out. So eventually, we will just have T d raised to the power k T inverse. I know how to do d raised to the power k. So that will become T times lambda 1 k, lambda 2 k, and the lambda 3 k T inverse. Okay? So in this case, system is asymptotic stable if and only if what? What's the condition? It's different from before. You just have this T and the T inverse. Because they are constant. It doesn't change with respect to K, right? There's some number like 100 or 1,000, but that's fine. Eventually, the asymptotic, the 渐进, the asymptotic behavior depends only on this one, because this term depends on K. If and only if all eggs lie inside unit circle, the same condition. Okay? There's nothing more. Nothing new. Any questions? It seems like eigenvalue determines the asymptotic behavior of our autonomous linear system without control. Okay. Unfortunately, not all the matrices are diagonalizable. For example, there's non-trivial space in between all the square matrix and the diagonalizable matrix. Okay? There's a final piece is some matrix not diagonalizable. For example, I give you a simple one. This one you cannot make it diagonal. Is this diagonal? It's upper triangular. 这叫什么？上什么玩意儿？上三角。倒三角，上三角啊？下三角，没有倒三角啊。Okay, it's not diagonalizable. I'm not sure whether you learned this before, but let's recall. I assume you learned, okay? Because I'm not going to cover that. Recall. All squares matrices. Some of them may be not diagonalizable, but all of them are block diagonalizable. Okay? They can be put into the so-called Jordan form. "叫什么约当标准型？这个学过吗？学过是吧？还记得多少呢？关键。Okay. They can be put into Jordan form. Okay, I'm not going to test the Jordan form in this class. I think it's an important concept. Diagonalizable matrix, those things can be diagonalized if these T are chosen eigenvectors. Okay? Diagonalizable matrix has independent eigenvectors. Then you can do TDT inverse. If the eigenvector space are smaller than the number of dimensions, then you have to introduce generalized eigenvector, generalized eigenvectors. That's become Jordan form, okay? So anyway, but in this case, I want you to take it as a fact. But in this case, we don't need to worry. The conclusions are the same. Although I cannot prove that for you, okay? Conclusion is the same. Actually, you can play with this guy. This guy raised to the power k. You still want, it's still about this, okay? It's really about the diagonal or the eigenvalues, okay? The conclusion is the same. What's the conclusion? Asymptotic stability is require, okay? Require all the eigenvalues. I'm summarizing in all the cases, okay? In all cases. In all cases, I don't know what's become more fancy than I need, okay? Anyway, so this is in all cases, asymptotic stable if all eigenvalues of A satisfies lambda I less than 1. Okay, the norm of it less than 1, so the inside unit circle. Or more precisely, this is strictly inside unit circle. Okay, this term is also kind of important. It cannot be on the boundary. If it's on the boundary, it doesn't converge. Okay, you have to make sure it stays inside, strictly inside the unit circle. Any questions? And I didn't want to jump into the Jordan form part. It's a little bit confusing and take a quite long time, but some people ask me offline, so maybe I will just talk a little bit more about internal stability today, okay? Before we continue the discussion on this controllability stuff, okay? Let's say more about stability. Okay, the things we didn't discuss in detail is that there's some case the system matrix A is not diagonalizable. All right? In this case, the stability also means eigenvalues of A has to be strictly less than 1, the magnitude. Okay. Let's just quickly go over this case, okay? So roughly speaking, asymptotic stable for linear state space model, we require the state vector, let's say A raised to the power k as initial state. If there's no control input, that's the response. Okay? Like the free fall of the ball, all right? That's the response without any control. And that need to go to 0 as k goes to infinity. The key is that for all x0 in Rn, you require, no matter where you start, you always convert to 0. That ability is internal stability. In here is asymptotic stable. Okay, we have assumed UK is always 0, okay? So then the stability test, you have to be able to distinguish what's the definition and what's a test condition. So when I ask you, maybe in the exam, what's stability? You cannot say eigenvalues of A lies in unit circle. That's the test. That's the condition for stability. The definition for stability is xk, the whole vector convert to 0. Okay, the stability test is egg of A inside unit circle. Okay, in other words, the egg of A, there's so many eigenvalues, all of them, the magnitude has to be less than 1. They could be complex number, so that's why we set unit circle on the complex plane. Okay, so let's talk about the most general case. Let's discuss this theorem in the most general case. In other words, I'm going to prove it. Not really prove, I mean, hand-waving proof. For you, the most general case. Because the last time, I think some of you, I asked you, have you heard about Jordan form? I think you have learned this, right, from your linear algebra, so I can mention this. So it's not a big deal then. For general case, I would say, if you still remember that, my figure here, there's some matrices are diagonal, some matrices are diagonalizable, okay? But they are not all. All the square matrices are block diagonalizable, right? So A can always be written in Jordan form. A can always be written in the Jordan form as A T J T inverse. That's a similarity transformation or change of coordinate. A is similar to J, where J is Jordan form of A. Okay, a special case. This is the most general case. All the cases we discussed last time is a special case of this one. So when A is diagonalizable, if A is diagonalizable, then J, the Jordan form, is diagonal matrix. Okay, it's diagonal matrix. So it's the same as the previous case. It's a diagonal matrix. In other words, all the Jordan blocks are of size 1. Okay, if A is not diagonalizable, then J is Jordan form. What do you know Jordan form? Or do you still remember? You must know, but you may not remember anymore. So there's several blocks, right? Those are Jordan blocks. It could be many. And all the others are 0. This is block diagonals. These are Jordan blocks. Those are Jordan blocks. Okay. I will review the structure of the Jordan blocks later. But let's first look at, if we can write in this form, then what we can say is that all we care is about what? X at time k. The state vector convert to 0, right? So A raised to power k times x0. Okay? So now I know A is this form. Okay? A is this form. So that means Tj T inverse, that's my first A. I need to time it times itself k times, right? Tj T inverse all the way. Okay, how many times I need to multiply? K times, right? And this is x0. So eventually, you will see these canceled out. Okay, it's similar to the diagonalizable case. That's Tj raised to power k T inverse times x0. That's fine, right? So, but this is a block diagonal. You can still write this as, let me just write it. So this has become T times, because J is block diagonal. So if you take power k, so the block multiplied by itself, all right? So it's J1 raised to power k, J2 raised to power k, this rule raised to power k. All the others are 0, T inverse times x0. Okay. So I want xk to convert to 0 for all arbitrary, for any initial state. Okay? What's the requirement? All the Jordan blocks have to convert to 0. Every element of this matrix has to convert to 0. If there's one element doesn't convert to 0, I can always find an initial state. When you multiply that matrix, you pick that non-convergent element, then it's a contradiction. You have to have every element of that matrix to convert to 0. Okay, so let me say that. So we need all Jordan blocks. Jordan blocks converts to 0 as k goes to infinity. Okay, now the question boils down to how can I guarantee all the Jordan blocks convert to 0? So let me give you a number or numeric example of J. So J could be, I'm picking arbitrary. Let's say this is 1, this is 2, 1, 0, 2, 4, 1, 0, 0, 4, 1, 0, 0, 4, negative 1, and all zeros, others, okay? How many blocks I have? You've seen Jordan forms before, right? There are 4 blocks or 3. 4 blocks, okay? So the way I write it, I already tell you the answer, but that's bad. This is 4 blocks. This is okay. So this is my J1, this is my J2, this is my J3, this is my J4. J1 and J4 are blocks of size 1. Okay? It's still a Jordan block. If all the Jordan blocks are of size 1, then it's diagonalizable. All right? So if I write this form, there's no other way you can further reduce it. Okay, this is a Jordan block. Okay. So now the question is that the Jordan block of this form, how does it evolve if you raise it to the power of k? Okay, so let's say let's prove by example. Okay, so let's say I have a 2 by 2 Jordan block, 2 by 2 block. Okay, so let's say maybe this block. Okay, 2, 1, 0, 2. Let me just write like a lambda I, because those are diagonals. Those entries on the diagonals of Jordan blocks are also the eigenvalues of A, right? So this is a generic Jordan block of size 2, all right? So if you raise to the power 2, can you multiply? So this times this is lambda I squared. And this is 2 lambda I, this is lambda I squared. Okay, if you reach to the power 3, you can use ji to multiply ji squared again, so you find lambda I cube. This is 3 lambda I, 0 lambda I cube. Okay, in general, I would say raised to the power k, you will have lambda I. You can summarize this formula. So this is k times lambda I raised to the power, no, there's no k times that. Oh, I think it's wrong, right? So this is a cube, okay? This is lambda I. This is k minus 1. This is lambda I raised to the power k. Okay, now I ask you, under what condition all the elements convert to 0? Okay, so Ji, the whole thing will convert to 0. When I say a matrix convert to 0, I mean every element convert to 0. Okay, I'm making a very strong condition. If and only if this lambda I inside unit circle. Okay, there's a slight kind of possibility of have some confusion in this term. Okay, this term k times lambda I k. All right, these two terms all change over k. Okay, k increase linearly. This is k, this is t, this is k, this is k. All right, and but this guy, if lambda I is less than 1, this is k, this is lambda I raised to k. So this norm will converge exponentially. Okay, something diverge. Multiply by something converging to 0, the overall effect still converges to 0 because exponential converges much faster than polynomial. This is just a linear even, okay? It's a first order polynomial. It's fine, right? Okay, so that's block size 2. If you have a 3 by 3 block, things become interesting. And I'm not going to multiply this for you. So the Jordan block of size 3 will be lambda I 1, 0, 0, lambda I 1, 0, 0, lambda I. That's a standard Jordan block of size 3. Okay, I will use my favorite term, verify yourself. Okay, that's my favorite three letters in this class. So Ji raised to power k would be, sorry, I need more space. So maybe I can zoom in, that's fine, okay? Ji raised to power k, in this case, is lambda I, k diagonal are fine, okay? Lambda I, k, and lambda I, k, okay? All the things below are 0. Here is off diagonal. It's one index away from the diagonal. So this part is k times lambda I, k minus 1. Okay? This is also one index away from the diagonal. This is also the same. Okay? This guy is 2 indexes away from the diagonal. All right? It becomes k times k minus 1 divided by 2. 2 is also equal to the 2 factorial. 这个连乘你们知道是吧 ？Okay, lambda I k minus 2. That's it. Okay, it's not too complicated. All right, let me draw 3 shapes. Okay, this is a triangle term. This is circle. This is square, okay? I'm not sure whether you can see the trend. So I would say circle is a derivative of triangle term, okay? With respect to k, no, with respect to lambda. And you can also say square is derivative of what? Circle divided by 2 factorial. There's a scalar difference there. Okay? So that's this term block. Okay? So if I want to say this guy convert to 0, I'm not sure whether you can still make the same conclusion. We need if and only if, I would say, if and only if what? Lambda I less than 1. The only complication here now is you have k times this. You also have some part, you have k squared times this. But no matter k squared or k cubed or k raised to the power 1,000, if you times a exponential, that exponential convergence will somehow dominate the rest. So the overall effect is also converged to 0. They may initially go up, but eventually go down. That's maybe possible. Okay, so now I can conclude, the theorem. So say, I hope that's fine. Okay, that's so the most general case. So we can claim asymptotic stability. The same claim, is equivalent to say eigenvalues of A less than 1. Okay, the same claim, but a little bit more in-depth discussion up to now. In case you want to play with Jordan blocks, Jordan form is useless. It's not what I said is. It's very useful conceptually, but in real world, it's not useful. Okay, Jordan form is only for you to understand something conceptually. It's not really for numerical calculations. You do Python, you even don't have Jordan in the typical NumPy, but in the SymPy, you can see my screen, right? Let's see. You may have to. Okay, so if I import from SymPy, import a matrix, that's a symbolic matrix and a symbol. I can use that to compute the Jordan form. For example, I can say this one. This is a 4x4 matrix. If you search online Jordan form, you always find this matrix. You always find the same. I can create another one, by the way. But just interesting because this is the one that used by Wikipedia. So everyone copy it. I want to change it, but I think, okay, that's fine. That's interesting. I will use it again. I will use it as well. So if you say A is the matrix, I plot A dot Jordan form, return this is almost like a T, right? T, J, T inverse equal to A. That's the Jordan form I'm printing J, right? So how many Jordan blocks we have in this case? I'm not sure whether you can picture this matrix or not. It's 3, right? 3 blocks. 2 blocks are of size 1. Okay? Each of them correspond to different the eigenvalues. Another one has an eigenvalue of 4, but the Jordan block size of 2. All right? That's numerical calculation. Now we can do symbolic. Okay? So I want to for what we just write down here, right? Let's say I can define symbols, A1. I can say lambda 1, but the lambda will be too long. I would say A1, all right? This is A2. A1 is, I define a matrix. This is standard Jordan form of size 2. The other one is standard Jordan form of size 3. Okay, it's the same thing like this one and this guy. It's just the lambda I have changed to A1, A2. Okay, I can print the first, let's say this guy is, that's symbol. I define K as a symbol as well, so they can compute the formula for me. Okay, this case is still readable, the formula. The double star here means the power. Okay, so a lambda I raised to the power K. This is lambda I, the A1 power K. Here is what? K times A1 K minus 1. Okay, the same formula we have used before. If I say the other one, I'm 2 raised to the power K. That's a little bit more complicated. But A raised to power, this is off diagonal, right? One index away, you have K times the lambda. This is A2 is the second lambda, okay? A2 raised to the power K minus 1. Here is K times K minus 1 divided by 2. times that. Okay, you can keep doing it. You can play with it. I will send this code to you. I mean, you can see how the things goes, and eventually you can remember. If you are 3 index away, you will have k times k minus 1 times k minus 2 divided by 3 factorial times lambda raised to the power k minus 3. If you can still generalize it in your mind, I wouldn't go over that. Okay? No matter what, you need lambda I to be strictly inside unit circle. Okay? If you talk about marginal stability, there's more complications. Okay? If lambda I is on the unit circle, then you require all the Jordan blocks to be at size 1. Otherwise, not all. I mean, at least the one that corresponds to the angle value on the unit circle, you want, because if this guy is 1, let's say lambda I is 1, this term will diverge. Okay? So marginal stability becomes a little bit tricky in state space form. But if we just focus on asymptotic stability, we're fine. Okay? So that's all I want to add for the internal stability. This thing I assume you haven't learned from your classical control class. The classical control is 经典控制哈，你们之前学的都叫经典控制。But you have learned stability. I need more pages. Sorry. Okay. What's going on?死机了。Okay. Let me save it first. Okay. Now I want to add a little bit more about, make some connection about the stability we learned in this class, state space models, versus stability you have before. What do you have learned before? Stability in classical control. In frequency domain, let's recall a little bit. So suppose you have a system, and you learn the system maybe in transfer function, h of s. Okay? The system is stable. If what? If the pose of this transfer function is pose of this hs inside unit circle. Oh, sorry. It's I would say open left half plane, right? So this real part of the pose, I assume you'll notice open left half plane. Okay, that means the real part of this pose are less than 0. Open left half plane. You have learned this, right? You smile. It's because you finally find something you learned before? Or you just like this? It's very simple test, right? Check the pose. And why?
Because the solution from
Solution, okay. This is actually, yeah, this is actually called the external stability condition, right? It's BIBO, but I will mention that later. But I want to say something that you should have also learned, but you claim you didn't, which is discrete time one, right? HZ. If in discrete time, this system, let's say discrete time, this is discrete time. Then discrete time system, you have Z transform. I reviewed it for you. If you haven't learned it or you forgot, you can check my review in the previous state space model class. But I assume you should have known this before entering this class. Okay, so HZ is stable if and only if the pose of this transfer function open left half plane. This is a unit circle. Okay? Unit circle. So And these two, this guy comes to here because of z equal to, so the open left half plane, if you define a change of variable, so z equal to e to the st, okay? That maps to the unit circle. The entire open left half plane somehow becomes inside the unit circle, okay? Okay, I assume those are the knowledge you know, and these are referred to the external stability, okay? I will call this. So this transfer function based stability is called external stability concept, okay? Stability. Or let's call it the bounded input, bounded out, the BIBO. I think you have heard about this before. So bounded input, bounded output. So internal stability, we don't have input. We don't care about input. It's really about your system itself, its internal state deviates from your equilibrium, how it performs, okay? External is about, okay, bounded input should give bounded output. How does these two relate? Okay, let's first, this is called the BIBO, right? So this, by definition, this means what? Bounded input must produce bounded output, okay? That's clear from the name of this stability test. Okay, what is a bounded? This is the condition, okay? So the bounded signal, let's say u of k, is bounded if u of k, the norm, is less than some constant for k, all k in, okay? It's something like this kind of signal is bounded by some number, okay? If you have unbounded, that means something like that. You can never have a constant to bounded. All right. So I want to emphasize, I think that's the key you have learned before as well. I want to emphasize one thing is that it's fine for output to be unbounded, right? If input is unbounded. So we only require, whenever bounded input, I need bounded output. If the input breaks our assumption, it's not bounded, then output shouldn't be bounded either. Okay, that doesn't break the condition. You see what I mean? I just need to make sure all the bounded input have bounded output. If the input is not bounded, I don't care. Okay, the system doesn't care. It's a reasonable request. Okay, so the key thing I want to say is, what's the relation? The relation, in lecture 2, we learned a way to change between state space form and transfer function. Okay, so let's say I have a system. If you define a system, even you call some packages in Python or MATLAB, there are different ways to describe the system, okay? The system in state space form, you have A, B, C, D matrix in linear system, okay? Discrete time or continuous, both are safe. System in transfer function form, So you have h of z. We are using discrete time most of the time in this class. Do you still remember the formula? We derived it before. It's c zi minus a b plus d. Oh, sorry, there's the inverse. Okay, this z is the z transform z. Okay, so this part is a transfer function in the variable of z. Okay, now my question is that what's the relation? What's the relationship between internal stability and BIBO external stability? I'm writing too fast today. I'm directly telling you the answer. I think you know it, or some of you know it. Let's say, I'll call it theorem. THM. It's my notation for theorem. So if system A, B, C, D, that means state space form, okay, is asymptotically stable. I have lots of abbreviations, but I assume that the meaning are clear, okay? Then is also BIBO. So asymptotic or internal stability is much stronger than the BIBO or external stability. Any questions?啊，后边同学有问题吗？你可以问啊，没问题，看不清也可以问，好吧？我写的太快了哈，可能是字又比较乱，其实是丑，但是说成乱啊。那个，所以写的慢点还能看清就行了。现在有点快啊，因为还是想把这个 stability 跟大家讲透彻一点啊。这个可能用处不大，但是我还是期望一个概念理解的稍微完整一点。OK， 所以你大概能跟你之前学的东西有个连接，这个还是你光一个点记住，可能这个用处不大，还是建立一个稍微一个小的体系会好一点，好吧 ？OK， I will slow down my writing. If system A, B, C, D asymptotic stable is also BIBO. The test for this is what? This means this part means, or i.e. what? This is eigenvalues of A less than 1 in the unit circle, okay? This part means pose of what? The transfer function matrix, which is h of z. The pose less than 1. Okay, so in essence, what we are trying to understand is the relation between the eigenvalues of A and the pose of the corresponding transfer function matrix h of z. It's maybe hard for you to think about their relation at first glance, but they are of course related. This guy is this, right? I already read this. Okay. If I want to prove this, I can actually prove it. It's very easy. Let's say how we can prove it. Suppose this is asymptotic stable. That means x less than 1. X of A. X means eigenvalue, okay? X of A less than 1. The norm. Okay, that's our condition. Now we can write down our h of z equal to c zi minus a inverse b plus d. Okay, this could be a transfer function or transfer function matrix. I think in lecture 2 we mentioned cases. I mean, matrix is nothing but from different input to different output transfer function, you put them into a matrix form. The only thing bothers us here is what? I think bothers you most is this guy. This guy has two challenging parts. One, it has inverse. It's hard for you to picture what inverse is, right? And B, it is a symbolic. It's a function of z. Okay? There are so many symbols here, but there's one key symbol. Z is a variable. All the others are constants, are values. If you plug in your system behavior, eventually have numbers. Z is a variable. You will never get rid of z. Okay, but I assume that you still remember. Not remember the details. At least remember you have heard of this. Okay. Zi minus a inverse. How do you compute a general inverse matrix?
Eigenvalue and the other joint.
Cofactor matrix of A, take transpose, divide by determinant of the matrix with Zi minus A. Do you remember this?
Yeah.
Cofactor 的伴随矩阵是吧？是叫伴随矩阵吗 ？OK， 伴随矩阵 take transpose。伴随矩阵是什么？就是你每一列都是把一行一竖。OK， 代数whatever that is. OK，let's call it cofactor. You can search it. Divide by the determinant of that matrix. Okay. Typically, you have a number for determinant, but here I can still compute the determinant of this matrix. It just become symbolic. Now I'm going to tell you or ask you to think this way. I think, do you recognize the form of this? Zi minus A. What is it? This is called characteristic 特征矩阵，对吧？ Characteristic polynomial 特征多项式是吧？是吧？ Characteristic polynomial of what? Typically you have lambda, but here z, right? You just symbolic change that lambda symbol to z. That's the same thing. Okay. So characteristic polynomial of z, that means determinant of zi minus a equal to 0 has n roots. These roots are polynomials, eigenvalues of a. Have n roots that are eigenvalues x of a. Are you with me? Suppose I have the roots is let me call it, okay, lambda 1, lambda 2, all the way to lambda n. I have n what? Eigenvalues. Okay, I have n eigenvalues. Each of them is a root of this equation. That means if you plug in it, it becomes 0. Okay, if you plug in that, it becomes 0. So typically you can factorize the polynomial as this becomes what? This becomes z minus lambda 1, z minus lambda 2. If I know the roots, okay, I can always write like this, z minus lambda n. These two are equivalent statements. Okay, if that thing has a root or n roots, each roots are I know the roots, then I can factor them like this. Some of the roots may be complex, and you have to have pairs. Okay, if you multiply this all the factor out, you have a complicated polynomial, and that polynomial is whatever that characteristic polynomial is. Okay, you can also write the polynomial in the factor form like this. Okay, so then I say these denominators, right? All the possible poles of H of Z come from here. Okay, so I can now make a conclusion. I hope I think that's detailed enough. All poles of HZ. You can think about this, okay? All the others are matrix multiplication. They only appear in not in the poles, okay? So all the poles of Z come from this part. Must be X of A. Okay, so that means because we say all the X of A less than 1, so then I will say poles of H of Z is also less than 1, so it's BIBO. Okay. Then I just claim a second statement. BIBO does not imply asymptotic stability in general, right? This thing is not, you cannot make the condition because what? Some poles, or say some eigenvalues, X of A, may not show up in the expression of H of Z. They may be cancelled out. Cancelled by the cofactor matrix or B or C. Okay? So you need to multiply by B and C. Some B and C may be, if unstable eigenvalues, they may not show up or survive after multiplying by B and C. I will give a quick example, maybe. We can have an example here. Example, let's say I have A matrix equal to 3, 1, let's call it. So this is 0.5103. My B is 0, 1. My C is 1, 0. My D is 0. Okay, if I don't mention D, that means D is 0. Okay, in this case, I can, let's take a break first. The next lecture, we will show you this one. Is an example. Let's continue the discussion on the BIBO stability. We have one last example that we need to consider here. Okay, suppose I have this system. First question I'm going to ask you is that, is it asymptotic stable? No, right? The answer is no, big no. Because eigenvalues of A, there is one stable eigenvalue, 0.5, and there's an unstable eigenvalue of 3. This guy is not in unit circle. We're in discrete time, okay? So that's bigger than 1 or not, that's the key that we look for. So now it's not asymptotically stable. But is this BIBO? It's hard to see now, right? The condition we derived before is the poles. Okay, so we need to see the poles of the transfer function matrix. Let's say the transfer function matrix, C times Zi minus A inverse B plus D, there's no D here. Okay, the first thing we need to see to calculate is this one, Zi minus A inverse. It's 2 by 2 matrix. That's the largest matrix you can calculate the inverse, I assume, by hand, right? Others, you need to look for numerical tools. What is it? So let's write it. This is Zi is Z00Z minus A is 0.5103 inverse. How to compute it? Just plug in, okay? So you have, this is Z minus 0.5, this is -1, 0, Z minus 3, inverse. How to calculate this inverse? Determinant. First, you need to find the determinant is what? Z times Z minus 0.5 times Z minus 3, right? So if I want to, and then I need to, I assume you can calculate. I will just write down the answer. Then I multiply this guy. That will be, yes. So what's left is where's -1? So this is 1 divided by Z minus 0.5. Okay, let me write down the answer. 0, this is 1 divided by Z minus 3. And this guy is 1 divided by Z minus 0.5, Z minus 3. Okay, I just symbolic calculate this. I assume it's right? If you multiply this, this is 1. It should be right, okay? Okay, so if that's the case, then H of Z equal to C is 1, 0 times this 2x2 matrix, okay? Times what? 1, 0. B times Zi minus A inverse times C, okay? So the only term survived is this guy, right? So will be 1 divided by Z minus 0.5. So the pole, they only have one pole, right? So the poles of HZ is 0.5. So poles of H of Z only have one, that's 0.5. That's inside unit circle is less than 1. So this guy is BIBO. Bounded input, bounded output. Okay? But it's internally unstable. There's some term, some internal state is out of control but did not show up in the output. Okay. Okay, that's conclude the discussion on stability. So asymptotic stability implies BIBO, but you need to see more. Okay, and the BIBO, the converse is not true. Okay, for us, it's important for you to know asymptotic stability. That's what state space form is what we care the most. Any questions? Now we know how to analyze stability of a closed loop or autonomous linear system. Okay. So the next step is how do we design controllers? Okay, we are not going to learn how, but today we're going to introduce another important concept, which is called controllability. Is whether you can design a controller to do what you want. It's the solvability of the problem. You first need to check, if I give you a system, you first need to check it's controllable or not. If not, you're out of hope. There's no hope you can do good results, okay? Then you can just tuning your controller without getting your desired result maybe in a year or two. So you have to check whether the system is stable, controllable or not. So a little bit abstract, but I hope you can stick with it. Let's first introduce another non-trivial fact, which is called Cayley-Hamilton theorem. 你们听过这个吗？讲过，什么东西讲过？现代 linear algebra 讲 Cayley-Hamilton theorem 吗？啊？真的吗？你在哪学的现代？I think some textbook does have it. It's a kind of important thing. Okay, I think I have a typo here. I need to correct this. Okay, this is, I think it's alpha 0 I, alpha 1 A, all the way to alpha n minus 1, n minus 1, A raised to n minus 1. Okay, the theorem is, or the fact that I'm asking you to know is for a square matrix A, n by n, okay? A raised to the power k for arbitrary k may be larger than n, can be written as a linear combination of 8 raised to the power less than n minus 1, less or equal to n minus 1. Okay, I'll give an example that will be clear. Suppose I have a 2 by 2 matrix. In this case, n is what? 2. Okay, then I ask you, say, what's A raised to the power 10? Somehow I got it computed. I have it computed before this class. So its number is like this. So we can always write A raised to the power 10, this number, as alpha 0 I plus alpha 1 A. Is this surprising? You don't know, you have no sense. Of course, if I say A raised to the power 2, so no matter what's the power you are raising, okay, but the higher order powers can be written as a linear combination of lower order powers. Okay, that's the key for this. So for example, in this case, we can just play with it. So alpha 0 times identity, which is alpha 0, right? Plus alpha 1A, which is, I'm going to write it down completely. That will be plus alpha 1, right? This guy is minus alpha 1, minus alpha 1. This is alpha 0 minus 2 alpha 1. Are you with me? And parameterize this matrix in terms of alpha 1 and alpha 0. Okay? How many elements I have? 4. Okay? So I want it to be 3, 65, this, 1, 1, 55, 38, 42. That's what I mean, right? If it can be written in this form, I can always find alpha 0 and alpha 1. That should be the case. But I have 2 unknowns. I have 4 equalities. Can I solve it? In general, no. But here, yes. So that's the surprising part of Cayley-Hamilton. Of course, if I gave you arbitrary equation like this, I throw numbers arbitrarily, I don't think you can find solution always, right? But if those numbers come from A raised to the power something, then I can always find this, okay? So that's the key. In this case, if you trust me with your student, because I'm really bad at numbers, so this is the Oh, yeah, that's right. So 1 negative 1159 and alpha 0 is 1524. My favorite term. Verify yourself. You can check that's the case. So Low's number has to be given by a raised to the power something. Then you can solve it. If not, you cannot solve it. Or you cannot guarantee to solve it. So that's the key for Kelly-Hamilton. For example, if I say A equal to 1, 2, 3, my another favorite matrix, 4, 5, 6, 7, 8, okay? Then I can say A raised to the power 100 is always identity this A and this A squared. Okay? So if you compute, this will have 9 elements. Here I have 3 variables I can play with, but I'm guaranteed to find solution. That's what Kelly-Hamilton says. Okay? It's not trivial. It's highly non-trivial, but it's an important fact for what? For square matrix. Kelly-Hamilton. Is this what you have learned? 差不多啊，现在2讲的，最后一周。OK。
I think the proof of this theory should be required by linear algebra.
Okay, otherwise you don't remember. Okay. Anyway, I think you know the fact is I don't want to go through the details. I just want you to know the fact. There's some mathematicians prove it. You don't need to prove it. Otherwise you become mathematician. But at least you are qualified control engineer. You know the result from mathematician. Okay, you can understand it. All right. Any questions? No question. We jump into the next topic. We're going to use it later on, but not immediately. Now let's introduce an important concept called k-step reachability. Okay, if you want to control something, you want to say whether I can, let's say, move my system to there, to some part in the state. That's related to the controllability and also related to the reachability. And let's define another term called reachable or reachability. So here is a x0. And this is some final location, xf, in the state space. Okay, the question I'm going to ask you for solvability is whether I can control my system from x0 to xf. That's a valid question, right? But if I can, that means something. I can control this guy to xf, a particular xf. But control requires time because we are dealing with dynamic system. The control effect need to be accumulated over time. Okay, so maybe this guy is fine. So maybe that depends on how many steps I allow the system to evolve. Okay, so if I can reach xf in k step, then xf is called k step reachable from x0. Let me repeat or clarify further. So xf is k-step reachable from x0 if I can find control control sequence to drive the system to xf in k-step. Okay, you perfectly land at xf at the time k. Okay, that's a very, very basic block to understand your controllability of your system, how controllable your system is. But we can just analyze your the system behavior. We can answer this question, okay, by giving some conditions based on the system model. So let's start analyzing or answer this question. If I ask you to answer this question, how do we start? Can the system reach xf in k-steps?
I think we can investigate if xf in the domain of maybe the range of on K-step input or output.
If I ask you to do this, you just need to start thinking from pure definitions and some common sense. There's nothing more shortcut, okay? So I ask you whether there's a way that you can move to XF in K-step. You just say, let's see. Okay, let's see how the system evolves. For example, I know the solution, right? At time K, my solution is like this. Is that true? The first one is 0 input response. The second one is 0 state response, depending on you. Okay. Now I want to use a little bit more compact way to write it down. Okay. So let's see. Let's say in matrix form, I can move this guy to the left. So this is xk minus a raised to the power x0 equal to this all the terms. Okay. But all the terms I want to write them in the matrix form, which will be b u of k minus 1. Okay. The next term, ab, this is the block basically. Okay. This is uk minus 2, and you can think about this a raised to the power 2b all the way to a raised to k minus 1b. This is all the way go to u of 0. Are you okay with this? Matrix vector multiplication is linear combination of columns, but here the columns are block columns, a chunk of columns. If you think about this, suppose UK belong to Rm. Nothing is scalar in this class. Everything by default is vector. So this will have m rows, right? The second UK minus 1 has m rows. At any given time, your input is multidimensional, has m elements there, okay? So overall, this will be what? This is how many? K times m rows in total. Okay? Uh-huh. Yes. 这整个也是个列向量啊。列向量就没有行了吗？列向量就是更多是 rows， 它只有一个 column 而已嘛。就说这个是列向量有 m element，OK？ 下一个列向量也有 m element， 最终有 k times m element， 也就是 k times m rows，right？ One column. And here you have m columns. The B has m columns, right? A times B also m columns. Okay. Overall, I have k m column. Okay. So this is but it's n rows, k times m columns. All right. So I can define this as U, capital U of K. I can define this big matrix as capital M of K. And depending on how many K I have, right? So this is the time. So now the question I'm asking is a control question. Whether I can control the system from this particular state to another particular state in K time. That's the question I'm asking. This is a valid question to ask. Okay? Now, the question I ask can be transformed into a solvability problem for the linear equations, right? So we want to find, so our question is, we want to find U0 all the way to UK minus 1, so that xk equal to xf. I want to move my system or drive my system transaction to xf. In other words, we want to fundamentally we want to solve equation xf minus a raised to the power kx0 equal to mk times capital UK. This is our unknown. Okay, reachable or not, it's nothing but tell me whether the system has a solution or not. It's the solvability of a linear equation, right? That's why we start reviewing those linear algebra. Under what condition this system has a solution? Do I need to have a unique? No, I don't care about unique. I just want to solve it, all right? Whether there's one solution or not, what's the condition? You're smiling. Can you say it? 用汉语也可以，用英文也可以。
I suppose from the analysis, the UK is the linear transformation of XL minus 3
Okay, so let's see. So this guy is k m by 1. It's a vector. Okay? This guy is n by k times 1. N rows, k times 1 columns. Sorry, this is got wrong. Okay, sorry. This is n by 1, right? XF state space model, right? This guy is km rows by 1. Right? It's not square. M is not square, so you cannot talk about invertible or inverse, anything like that. So when you see matrix vector multiplication, always think about it as linear combination of columns of the matrix. So if we say it in plain words, it's nothing but, is there a linear combination of columns of mk equal to a given xf minus this? These are given, right? Those are given. These are numbers. In other words, whether this given vector is a linear combination of columns of mk, that means whether xf, these are unknowns. So this guy has a solution. This system has a solution if and only if I have too many blocks here. If and only if what? xf minus a k x0 belong to the column space of mk. Column space is the range, right? Column space means linear combination of columns of that matrix. I think we reviewed it before, even exactly this same kind of problem, okay? So the reachability lemma that I call a lemma is not that hard. It's the final state is k-step reachable from x0 if xf minus this guy belong to the column space of this BAB a raised to the power k minus 1b. Okay? So this is nothing but this guy is the column space of mk. Range is the same as column space, okay? So I'm using different terminology. Are you with me? So what does this mean? You want to get here, but somehow you have some initial condition will have some kind of a leftover behavior, okay? You need to, it's gradually cool down maybe, but the difference you are making is due to controls, right? And that control vector is just how much you want to control to make, all right? How much distance or deviation you want to control to contribute. That has to lies in the column space of this MK matrix. Let's take example, look at the example of simple case. A equal to 2 to B equal to 1, 1. X0 is 0, 0, okay? You start from the origin. I'm asking you, find out what state is reachable in 1 step, 2 steps, 10 steps. Let's say 1 step. Do not plug in lemma. I want to start from definition and the key kind of linear algebra theorems. So x1 equal to the first 1 step, right? x1 equal to x0 plus b of u0, right? Okay, so then, so the reachables are what? By choosing u, the u0, what control you apply, you can drive x1 to what? To anything like the u0, u0. So I will just say x1 in 1 step. So in one step, the terminal f can be anything like alpha alpha or some alpha, right? Depending on what you choose. This is in 1 step. In other words, I have 1 step belong to the column space of B, which is just alpha alpha. In 2 step, what we're having is x2 minus a raised to the power 2 x0. X0 is 0, so this term is 0 as well. So you have b, ab times u of 1 and u of 0. Okay, that's how the matrix was constructed before. Okay, this term is 0, right? So all the reachable x2 are in the column space of B, AB. Okay, so if I want to write a little bit more details, so it will be B is 1, 1. What about AB? 2 and 2 looks weird. This is U1 and this is U2. So by changing U1 and U2, you are essentially obtaining different linear combination of columns of this MK matrix. So I can say in 2 steps, x2 will belong to the column space of this 1, 1, 2, 2, right? But this is the same as the column space of 1, 1. It's the same. Okay? So how far you can go, you're still somehow not only get to alpha alpha, you cannot get to anything other than this line, right? The 45-degree line. 10-step reachable, what do you think? So the reachable state will be xf. I will skip those intermediate steps. xf will be in the column space of B, AB, all the way to A9B. okay? But in this case, because B is 1, 1, AB is 1, 1, 2, 2. If your A squared B will be something on the same space, eventually you can conclude that's the same thing as the before. So this system is bad. Okay, somehow it gets stuck. No matter how hard you control it, it always stay at the line here. Okay, you start here, all the part you can get to is this line. Somehow your system is limited to that space. If your boss asks you to control the system to here, to other points, you should immediately give up, right? Otherwise you get stuck. And you should show him the system. The control reasonable state is here. You cannot ask me to do something that are not reasonable. Okay, so this system is bad. Are there those kind of bad systems in reality? A lot. Plenty. Okay. Now we have a good system here, but now I have a multidimensional input. Let's take a look of this example so that you have a better sense of what I mean. Now I ask you, what is the one step? Still, what is the one step reasonable state? What is it? So the column F, in this case, I'm still saying zero initial state, okay? So XF will belong to column space of B. That's it. Okay, what's the column space of B? R2. So what does this mean? All states in R2 is one step reasonable. Okay. Suppose I pick XF equal to 1 and 2. That's my desired location. I want my state to be, okay? So then I need to, because everything is one step reasonable, I can find at least one control at U0 to drive me there, right? I want to find this control. So I will say 1, 2 minus A times initial state with 0, 0 equal to this A, right? This is the A. No, B. B is the 1, 1, 1, 0. That's my B. Times my input U. So U is U1, U0 of 1, and U0 of 2. What does this mean? It's that I have two input dimension at time 0. At time 0, I have two input. At any given time, my input, the number of input is it's dependent on the system definition, right? In your car, at any given time, autonomous vehicle, maybe depending on your assumption, you could have acceleration and also steering angle. Those things has to be assigned at every time instant. Okay, you may have multiple input. So, so you need to find this guy, and can you find them? Of course, you are, right? It will be, for example, it will be 2 and the negative 1. That will be, I think, 2 times this. Yes. For example, the U2, let's not say for example. This is U of 0 equal to this. I just want you to get used to notation that everything is vector. No matter, there's a time index. Also, there's dimension index. Sometimes I'm not going to say everything very, very from the beginning. So I assume you are used to those notations. Any questions? Okay, now you can tell whether a system is controllable or reachable in several steps or not. Okay, now let's go to the thing we care about. Okay, so let's finish this definition. So all we did so far is trying to introduce the definition of controllability. Controllability is nothing but you can reach any point in the state space from any point in the state space. You can infinite time steps. So the system A and B, why I call A and B, that has nothing to do with C and D. Okay, the system condition has nothing to do with C and D. So I want to say a system is controllable if any state xf is reachable from any initial state x0 in finite time steps. That means your system is controllable. That's a definition somehow works well in discrete time. Okay? So in other words, any initial state and we can find control to steer the system from x0 to xf in finite time steps. So that's ability to do control design. Okay? Did I say how do you do control? I didn't say, right? No matter how you design a controller, this is about the limit, whether you can, there's a hope for you to solve the control problem or not, okay? And according to the reachability lemma, this requires xf minus a raised to the power x0 stays inside the reachability. This is this column space, right? So this is nothing but column space of mk that we defined. Okay, mk. Okay. The key here, and I hope you are becoming sensitive to those key terms. The key terms is also this for any. That's the strong requirement. If you just find one, it works for some initial state, some final state. It doesn't mean much. All right. You have to be able to make it work for arbitrary. That's the key word. Okay. So for any, this symbol means for any. Okay. Have you said this before? Okay, then that's fine. For any initial state and any definite state. So that means xf can be arbitrary, x0 can be arbitrary. Two arbitrary add together, you got two arbitrary or just you got one, right? So this vector is just arbitrary. Arbitrary. Right? Arbitrary. Okay? So in other words, arbitrary vector in Rn has to be in the column space of Mk. That means the rank of Mk has to be equal to n. Okay? So that means the rank of this Mk matrix has to be equal to n. Because that's rank means what? Number of independent columns. Okay? So this has to be n-dimensional. Okay, we'll explain or complete this part next time. If you're done, then we go back to the controllability that we introduced last time. Do you still remember? We first cover an important math property, Katie-Hamilton theorem, says that a raised to the power k can always be written as a linear combination of identity a up to a raised to the power n minus 1. No matter k is 100 or 1,000, at most you need n minus 1, where n is the dimension of a. Okay, a is n by n matrix. Okay, then we start defining, so what we're trying to do is try to see whether the system is controllable or not. And controllability means
the system can reach the state or reach any state possible.
controllability we define here, okay? A system is called controllable. 你这个系统可控，你觉得应该怎么定义？ 就是这个我怎么玩都行，对吧？我从哪儿到哪儿都可以。So from any initial state, I can design my control input to drive my system to any or arbitrary final state within finite time steps. Then the system is controllable, right? That's the definition. Okay, that's the definition that makes sense, intuitive sense. And from the definition, and also from the solution of your state trajectory, we can start analyzing what does this imply. Okay, so my system response has two parts, right? One is due to the response of initial state, the zero input response part. And all the rest are the contribution due to the control input over time. Okay, last time we start writing it like this matrix vector form. So this right-hand side is the contribution to your state trajectory due to your control input. The variables are your control input. Okay, you can design input. And then your system state will be driven to different locations. Now I'm asking, or we are asked, to design controls to see whether the system can be driven to arbitrary state. Okay, that means this part has to be arbitrary. That means I have to be able to use this vector so that the multiplication can be made arbitrary. Okay, so whenever you see this matrix vector multiplication, you always think about it as linear combination of the columns of this matrix. Okay, B, A, B, A raised to the power 2, B, and all the way to A raised to the power K minus 1. That means you have K steps. Okay, so whenever I want to, okay, we go through the reusability lemma. Let's not repeat everything, but let's start from here. I think that's where we stopped last time. If I want my system to be controllable, that means I want this guy can be reached arbitrary in Rn, then I have to make sure B, A, B, A raised to the power K minus 1B, suppose I have K steps, okay? K is arbitrary. Has to contain the entire Rn. Okay? So that means the column space, this column space has to be Rn. Has to be Rn. This is what? This is, did we say that before? This is how many columns? I have K times M columns. All right, and I have N rows. Okay, this, and also N rows. So this matrix is really fat, okay? Fat matrix. So the column space of it has to be Rn. Because column space is all the possible linear combinations of the columns. Okay? If all the linear combination columns contain Rn, that means you can reach arbitrary locations in Rn. I think that's enough for this discussion. Okay. The range of this is Rn means the rank of this is n for some finite k. Because the rank cannot be bigger than n because you have n rows, right? You can keep increasing the number of columns. You can have 1,000, 1 billion columns, but you only have n rows, and the rank eventually you have to have n. Okay, rank means what? The number of independent columns of this matrix. Okay, one way to check this, so if we want to have stability, if we want to make sure this is controllable, we want this rank to be Rn for some k. And we know how to compute rank, right? At least in MATLAB or using numerical tools, you know how to do it. So one way to check controllability is just keep increasing k from 1, 2, 3, 4 to see whether this B, A, B all the way to A is n or reaches n or not. Okay? But I say finite time k steps. Finite steps, I didn't say what's the largest I can accept. So eventually I can keep going, right? But by the Cayley-Hamilton theorem that we introduced last time, there's no need to check for k bigger than n. Okay, so let's discuss that. That's called controllability test, and give us the definition of controllability matrix. That's an important quantity in control theory. So AB is controllable if and only if the controllability matrix, MC, it's a matrix, controllability matrix, defined whenever I have this small triangle above the equality sign, I mean define. Define means what? Define means my definition, okay? You can define arbitrary other things. Define means I don't need to explain why it's the case. You can define arbitrary things. The key is that whether that's useful or not, okay? So here is the definition. B, A, B up to N, A raised to N minus 1, B. Okay, A is in our N by N matrix. B is N by M matrix. That's our convention. Okay. So controllable means the controllability matrix here. See the difference. There's N before our condition is what? K. Okay. K can be, I need to make sure I can find one K. Okay. But here I only stop or have a fixed number, which is the dimension of the state space. Okay, it's full rank. That means the full rank means what? This is rank of MC is N. That's full rank. In this case, I have more columns than rows. Full rank means the number of independent. At most, I can have N. So full rank means MC is N. Okay, let's argue through that. So let's somehow prove it. Okay, so controllability. It's controllable. Okay, let's not say controllability. So controllable. The system is controllable if and only if, in the previous slide, that means the rank of what? Of B, AB, all the way to A raised to the power K minus 1B equal to N for some finite K. You don't know how many steps you need, but you can keep increasing K to see whether I can reach. If I say I give you one step, you say not enough. If you give me 2 steps, I can control arbitrarily. And then I can increase K equal to 2. You say, okay, I may need 3 steps. You keep increasing this until you see I can cover the entire space with K steps. Okay, that's somehow we argued that before. But by the Cayley-Hamilton theorem, Cayley-Hamilton theorem implies rank of B, AB, all the way to A raised to the power K minus 1B equal to rank of B, AB, AN minus 1B for all K bigger or equal to N. You see the where I'm going? So this guy is our MC, controllability matrix. I stop at the dimension of the state. I don't need to increase more to check. If say the system is not controllable in, I cannot reach arbitrary state location in 10 steps. Then you can directly say, sorry. That means you give you more steps, doesn't help. If your state dimension is less than 10, for example. Okay, I can briefly mention that. So why this is the case? Because just show you one case. Suppose k equal to n plus 1. So rank equal to k. I mean, these two are equal. If k equal to n, of course, these two are the same when k equal to n. All we need to say is k bigger than k, n, right? Let's say k equal to n plus 1. Then I say I'm k. I will call this guy I'm k, right? So b, a b, all the way a k minus 1 b. That's I'm k. K minus, this is, let me write it in terms of n. So there's n minus 1 b, and there's also a n b. Suppose I call this guy I'm k. I'm not sure whether I defined it before. I think so. I defined this on previous slides. I'm k means this form of matrices up to k steps. Okay, if I k equal to n plus 1, then let's have one more term, a raised to the power n times b. So we know a raised to the power n by Cayley-Hamilton. Okay, we know this can be written as alpha 0 I, alpha 1 a, all the way to alpha n minus 1 a n minus 1. Okay, we explained that at the beginning of the last lecture. So no matter what, this is n plus 100, you can also written this, but the coefficient may be different. Okay, that's the key. That's Cayley-Hamilton theorem. This implies this term, okay, a raised to the power n times b. Let's say my b is b1, b2, all the way bm. How many columns I have? M columns, right? So this guy will be a n b1, a n b2, all the way to a n bm. So a raised to the power n times b is n by m. Oh, this is n by m matrix. This is n by m matrix. I have m columns. The first column is a raised to the power n times the first column of b. Okay. Oh, sorry. So whenever you see matrix vector multiplication, it's a linear combination of columns of A. The matrix A raised to the power n. Okay, so I can claim, or you can, I think it's this B times B is just this form. Okay, I would say I can make this claim. I don't want to further prove anything. We can argue that it's a linear combination of columns of MC. Okay, this guy is MC. Because these two facts. Because for example, this guy. Okay, this guy is a linear combination of columns of AN. But AN is this. Okay? It's a linear combination of this, linear combination of alpha 1 times A, linear combination of A n minus 1. All right? All of these columns already appear here. Okay? There's nothing more because all of this is here, right? So it's a linear combination of columns of MC. So adding this guy doesn't increase the rank. Okay, so that's why MK, the rank of MK, still equal to the rank of MC. I'm not saying MC is full rank already. No matter what rank MC has, adding this term only add some dependent columns, okay? Dependent vectors of previous columns. I think you need to think a little bit after class. All it means you can stop checking after k bigger than the state dimension. All right, I think that's enough. Let's see some numerical examples. First of all, let's say that I have a 2x2 matrix, two-dimensional state space model. In this case, n equal to 2, m equal to 1. Okay, so I want to ask you whether the system is controllable or not. And I can say MC equal to, what is MC? B is 1, 1. A times B, MC is B, AB, all the way to n minus 1 B, right? So A times B is 2, 2. Okay. So rank of MC, what is the rank of MC? It's 1, less than 2. Is this full rank? So uncontrollable. Okay, you plug in the test, it's uncontrollable. But you may ask, who cares? What does this mean? You can get a perfect score at midterm or final exam by checking it, but you may not draw any connection with what it means. Okay, so I think it's important for you to know its meaning. We already explained the meaning, but I want you to somehow, when you review this, does not say, okay, I see how to calculate this, but you need to know what its meaning. Okay, for example, I'm just giving you an example how to understand the meaning, okay? So this means uncontrollable. What this means? MC not rank? That's not meaning, right? That's test meaning. Meaning means, as Yuntian said, it's uncontrollable. There's some part of space I cannot go. Okay? That's all it means. And with MC, you know exactly where you can go and where you cannot go. Everything is characterized. So in this classroom, let's say, there's some part my controller can drive to, and the other part my controller cannot. So you know the limitation of your control. So you wouldn't make somehow unrealistic goals. That's kind of important sometimes. Well, let's say example, you like numerical example. Let's say initial state is 0, okay? And my final state, suppose I want to go to 3, 3. Okay, we can check xk minus a raised to the power k x0. This is the initial state minus the initial, subtract the initial state. That's the control contribution you have to make, right? And that will be b, a, b, all the way a minus 1b times what? u0. This is k minus 1 all the way to u0, okay? So it's too small. But you can easily verify in one step. Let's say one step, x1, this is 0, right? So you have x1 times b times u0. That's b is 1, 1 times u0. Okay, can you choose u0 to make x1 to be 3, 3? So we can choose u0 equal to 3. That means then in this case, x1 is 3, 3. Reach this guy, okay? What I'm talking about. So there's some part of the space I can reach. Okay, but you told, we just said this system is uncontrollable, right? If we pick, but if we pick xf, let's say we want to go 2 and 4. Can we do it? Can we find control to do it? Okay. If we pick this, I need to somehow jump through here, okay? If I pick this, then we can never reach xf for any k. You cannot reach it not because you're not given enough time. Okay, it's because the system is by default or by design has some kind of limitation. Can never reach this for any k. I think you know what it means, so I will not further. So this system is uncontrollable. That means some part of state you can still control, get there, but there's some existing space or part of the state space you cannot get to. So your system is uncontrollable. Okay. So let's go to the next question. So this guy is a little bit different. Now I have this guy is n equal to 2, but I have 2 inputs. B is 1, 1, 1, 0. Now what's my controllability matrix? Do you recognize this? So B is block. Okay, you have to put entire B there. It's not just it's 1, 1, 1, 0. That's B. And how far I need to go? I need to go A, B, right? A times B is, in this case, it's 3, 1, and 1, 0. Become a little bit fat matrix now. So I need to check rank of MC. What is it? It's 2. Is this controllable? Is it full rank? But their columns are dependent on each other, right? Full rank. It doesn't matter whether there's some columns are independent. You have 4 columns. All you need to reach is in R2 because the state dimension is 2. So you have rank is 2 is good enough. So it's full rank. This is equal to n. So it's controllable. All right, you see how it works. This guy is n equal to 3, m equal to 1. The controllability matrix is 0, 0, 1, and AB. AB is 0, 1, 2. I think so, yes. And A squared B, you need 1 more, right? Because n is 3. So you need another one, which is 1, 4, 4. A times this 1, 4, 4. Yes. Okay. So this guy is rank of MC is 3 equal to the state dimension. The column space of MC is all the vectors you can reach, okay, by designing controls. Because control is nothing but you select control, you just try to find the linear combination of columns of MC.
This is controllable. All right, we finished controllability definitions, and I think most of people remember, or most students typically remember the controllability test. When I ask you what controllable means, typically people say controllability matrix has full rank. That's almost like memorizing some kind of conditions, but I want you to pay attention to the concept. What does it mean? It means some part of state is controllable or the entire part of the state space are reachable in finite time steps. Only if 更简单了。If and only if， 就这个东西一定要这个东西首先要这样。这个可以，如果是它是 full rank， 可以推出那个 k 减1的时候，它是可以也是 full rank， 但是为什么一定是 an 减1呢？没有说不 controllable if and only if this guy is there's 有很多不，你这么说吧 ，rank of n 这个到 n 也是 if and only if。那当然了，你会有很多这个 sufficient necessary condition， 挑了一个最小的，这是最少的，其实是 n 减2就不行了，因为 Cayley-Hamilton theorem 要求就是这个 Cayley-Hamilton theorem。第三个我们举的例子其实就是反例 n 减2。你看嘛。这个是到这儿是 n 减1嘛，就是因为 Cayley-Hamilton theorem have this form, so you have to have this, okay? So all the a raised to power k can be written up to n minus 1. 这 k 可以是我们之前举过10，或者即使 n 是2哈 ，k raised to power 10也能写成 alpha i 加上 alpha 1 a， 对吧？就不管这个事儿多大。就是你到 a 的 n minus 1这个 power 就够了 ，OK， 你要再多就没用了，也可以，就说其实就最少的了 ，OK。当然你要是 n step reachable， 那你 n 加1 step 肯定 reachable 嘛，你最后一步啥也不干就行了 ，OK， 它是这个意思 ，OK，now let's talk the dual concept, which is called observability. Again, I think it's most important for you to know the meaning of those definitions. And let's first discuss the definition of observable. 可观，你们听过这个词吗？没听过，这是 state space or modern control 特有的 ，OK。If you learn Kalman filter or use Kalman filter, sometimes the error covariance measure may diverge. Okay, there's a limitation. So sometimes the system cannot be observable. There's no way you can estimate the internal state from the output. Observability is concerned about whether you can use output to infer all the internal state or not, okay? So a formal definition of observability is the following, okay? So a system ABC is called observable if any initial state, okay, I'm circling out the key word here. Any initial state can be another keyword, okay? Uniquely determined given the system input trajectory and output trajectory for, again, some finite k. So if you typically you measure, input is something you send to the system, and you measure the output, okay? And there's possibility, there's internal state, because the system output depends on your input, also depends on internal state. Okay, the initial condition, right? If you can use the input-output pair to uniquely determine the initial condition, then the system is observable. Okay, if it is observable, you can design observer to observe its internal state or zero initial condition.
How to understand the uniquely determined?
There's no other solution.
No.
Yes. Okay. There's no ambiguity. It's not saying, okay, the internal state could be this, could be that. Then there's no way you know which one is right. Okay, it can be uniquely determined. That's kind of important. Okay. So from this definition, it's again from definition, and with our solution of the state space equation, we have the solution of this form, right? I think by now you should be familiar with the solution form. We can just, based on the solution, based on definition, we can start analyzing the conditions to ensure observability. Okay, so the output, the state response at time k, this is zero input response. This is the contribution due to controls, right? And now let's write it in a slightly different form. Okay. The way I somehow rearrange it, I put this term the first. Okay. So this is a raised to the power k minus 1, b. This is a raised to the power k minus 2, b, all the way to a, b, and b. Dot, dot, dot. Okay. Times. The reason I arrange like this is that now I can put my time index according to the positive order. Okay, this is 0, u1, all the way to uk minus 1. The same as before, this guy is m by 1 vector. Okay, you have m dimensional input. So overall you have, m by k, a big vector. Okay. Again, this guy, this is m rows. This guy a b is m columns. Okay, this is m columns. Okay. Now, observability requires or is concerned with the input-output. Now I need C, I need Y to discuss the observability. So I know Y0, you can see Y0, what is Y0? It's a C times X0 plus D U0, right? I think I'm running out of space. Let's say Y1 is, let me just use a parenthesis instead of square bracket, Cx1 plus Du1. Okay, so this is C times A x0, if you plug in the formula, and plus D times U, sorry, another C. C times x1 is C times B U0 plus D times U of 1. I'm just plugging in the recursive formula. Try to understand, right? You have a history of control input output. I want to know the initial state. Everything have to relate back to the initial state. And the Y2 is Cx2 plus D of U2. The output at time 2 is the state at time 2, and the input at time 2 multiplied by C and D respectively. Then you do the recursive formula. This is CA squared x0 plus CAB U0 plus CB U1 plus D of U0. Okay, I can keep writing like this. Okay, now somehow I'm able to cross the page, okay, to define a vector. Okay, this vector. I will call this y of k, up to yk, right? Let me define it more carefully here. So let's define capital YK as the following. This is Y0, Y1, Y2, all the way to YK minus 1. Okay, that's my capital YK. It has K input, but starting from time index 0, so it's Y, capital YK. And I can define my capital UK is the same as this guy, okay, this guy. So it's U0, U1, all the way to U of K minus 1. These two are what we have. Over time, you measure those things. You measure output, okay, and you measure input. What you don't know, or what you don't know for sure, is the initial state of your system. Okay, now let's say, now I can write these things out. Y0, Y1, Y2, all the way to YK minus 1. That's big vector, that's my YK, capital YK, right? From the summary we have here, C, CA x0, CA square x0. That's the first term that depends on the initial state. So I can write it like this. This is C times x0. Y0 is C x0 plus what? D times U0, right? It should be really big. Okay, that's my U of 0. The first row like this, right? Y0 equal to C x0 plus D times U0. Y1 is C. How does Y1 depend on x0? C times A times x0, right? So it's CA x0 plus what? CB U0. So that's CB times U0. Okay. Then I also have U1, right? So this is D of U1. So that's the second row. Okay, so of course those are all zeros. This is U2. If you want to lose K minus 1, okay, just this becomes 0. Just keep doing this. You can summarize the formula like this: C squared x0. This part is CAB. This is CB. This is D. Okay, after D is all 0. Okay, so those are diagonals. Up to here is D. All the way here, you got CAK minus 2B, CAK minus 3B, all the way to CB. Okay, here is a CA raised to power K minus 1, like this. Okay. What we can define here is this is my big matrix. This is T of K. I can call it T of K. This is my capital U of K that I just defined. This is my initial state that I don't know. This is, I call it OK. This is O of K. This is what? Y of K. A lot of notations, but they're tedious derivations, so I didn't spend too much time. I assume you can definitely derive this for sure. And arrange them in matrix form is also not that challenging. Okay? So now I want you to, how much time I have? 3 minutes? Okay. Now I want you to know what we're trying to do. Okay. What we're deriving so far, you may get lost. Okay, so what we're doing now.
Linear equation about x is 0.
Okay, so we want to understand the observability of the system. Okay? Observability requires you, okay, I know control input, I know my output measurement, I want to know whether I can uniquely determine initial state. Okay, the more output, the more data I have, the more equations I can use to infer my internal state. Okay, so what I'm given is C, A, B, C, D, all those things are all given. All right, so these guys are known, right? This is known. These are known. This is known. And also this is known, right? All these are known. This is only unknown that I need to solve. Okay, observability, if you write the system equation down, it just becomes a linear equation and whether you can find a unique solution or not. Okay, typically your system states are more than what you can measure. A simplest case is your car. Okay, your car. Let's say your car traveling on the highway, and you can measure its. Let's say you have GPS. You can measure its position. Okay, but what affects the car's motion include many other things. For example, could be the velocity, also important, heading angle. Okay, steering angle, whatever, those things. So can you use some measurement, which is only a subset or even a function of the state, to infer the whole state that impact your future motion? That's very important, okay? Some cases very simple to see it. Some cases is highly non-trivial to see whether that's possible. Whenever the system is observable, that means you can use your output measurement to infer the entire state. For example, if you can measure the position of your car, you can infer, I don't think you can infer, if your system dynamics is a basic model, like it has a steering angle typically is input, okay? So those are I don't think you can infer that, okay? So then your system model is, either model is selected is incorrect, or you need to improve or add more measurement. Okay, before you can design your controller. You need to add more measurement to make sure your system is observable before you can design your state space controller. Okay, I think that's all for today. Next time we'll finish this and start talking about how to design control and observer. Okay, 我们上节课开始讲了这个 controllability and observability. Controllability is relatively easy to follow and understand. You're just trying to move your system or drive the state of your system from any initial state in any final state in finite time steps. Okay, that's kind of a definition is a little bit intuitive to understand. But for observability, some students ask me about this definition, why it matters. So let's start today with a few words. I would say still not much, but a few words as why this definition makes sense. And later on, once you see design examples, this will become definitely more clear. But before we understand the concept and theorem, let's give some motivation examples or introductions to the observability definition. Okay, last time we start telling you the definition and start analyzing the conditions to satisfy the definition assumptions. But I think some people don't know why we need to define this way, why it matters. Okay, I will call this part motivating discussion for observability. Okay. So first of all, we are dealing with the standard model in this class is state-space model. Of course, you can change state-space model to any other equivalent models, okay? But state-space model is what we care and what we need to use to design our controls. And to design state feedback control is called 闭环控制, state feedback control. We will learn in next lecture in details. We need to know the state, okay, of the system, okay, state X of your system. That information is needed for you to design state feedback control, for you to use the modern control theory to design controllers. Let's assume you can accept this, okay, state is needed to simulate the future of your system and also to design your controller, okay? You haven't learned how to do it yet, but you can accept, hopefully, that this is needed. But oftentimes, we can only measure output, okay? And we have the measurement equation, which is, let's say, yk equal to cxk plus duk. Okay, that's everyone knows so far. The measurement is called, or the output of your system is called y. By defining this output, you implicitly assume that you can measure y, okay? Now some people may say, okay, y and x are related. If you measure y, I will already know x. But that's only when, in scalar case, of course, but in this, everything is vector, so it's a little bit non-trivial. So in the simplest case, let's say if C is square. By the way, C has to be, C is RP by N. Is there, let me think. What's our dimension index? X in Rn, U in Rm, Y in Rp. Okay, that's roughly my notation. In order for this to be square, you cannot change state dimension, okay? You have to ask, have as many, the P and N has to be the same, all right? This is a square and invertible, if this is the case, and invertible. Then everything is easy. So xk, we know it, would be C inverse times yk minus d of uk. Okay. In scalar case, that's true, but in general case, that's only true when C is square and invertible. Okay. in this case, it's almost like it's equivalent, I would say, to directly measure all the state. Okay? Right? Your output dimension is the same as the input, and they are invertible. So it's almost like you can uniquely determine state from your output vector by one output vector. Okay? But most of the time in state-space model, you realize that the system dimension or the state dimension is much bigger or higher than the output. So when C is not invertible, by not invertible, I mean it could be square non-invertible, or it's not a square matrix at all. You cannot invert it. Okay. So you cannot directly. So for example, yk, let's say start from 0. Okay, y0 is cx0 plus d of u0, and y1 is cx1 plus d of u1, dot, dot, dot. Okay? And so the question becomes now, suppose C is like this kind of matrix. All right, you have more columns, then you have 10 states, for example. You may only measure 2 of them. Okay, that's typical. Okay, I'll give you an example later. So there's a lot of ambiguity about xk's, right? About what x is. So the question would be asking is not, because I have all the sequence of output and all the sequence history of the input, okay, instead of restricting ourselves to just one step measurement, can we use multiple step measurement to infer xk? Mathematically or formally, I will write the question like this. So can we use input output history? Okay, 历史数据. Let's call it UK and YK. Okay, K from 0 to some finite number. Okay, let's call that capital N. Okay, this is finite number of input output history to estimate or uniquely determine x0, x1, all the way to x, whatever k currently. Okay, my notation is a little bit strange here. Let's use another index. Sorry. Let's say this is my dummy index. Here is uj, yj, j from 0 to k. All right. The current time step is k. And can I use all the past information to estimate the entire state trajectory? I want to know everything in the past, okay, up to the current state. The question is this. Is this possible? Now it's become a little bit non-trivial, right? So that's become non-trivial. But you see, so there's definitely more, I would say, more unknowns, right? But the problem is that x1 depend on x0, x2 depend on x0, and the u0 and the u1, right? So in general, I would say, note, all the xk's depends on x0 and u0 up to uk minus 1. So if I gave you the initial state, I tell you the input history, then I know xk for sure based on my model, right? We derive the solution. This part is known. Okay, input is something you send to your system. It's something you have control over. So you know these values. Okay, so now the question boils down to the following. So this question equivalent to the following question. Can we use uj, yj history, j from 0 to k, infinite k, okay? To estimate, let me say that clearly, uniquely determine x0. All I need to know, the only unknown here is x0. If x0 is known, I can use uk's or the input signal to determine xk's, right? The only thing I don't know is when I turn on the system, at the beginning, I can only measure output. I don't know the initial state, okay? Does this sound clear or familiar to you? This becomes our definition. This is exactly the definition of observability. Okay, that's roughly the logic. People start defining this way. Why we only care initial state. Why we need to do finite time step past input output history. That's the reason. Okay. You really need state to do involve to. We discussed state-based model before. You have to know your state, current state, before you can evolve into the future. Okay, before you can do any prediction based on your model. And in addition, your control strategy often use full state. That's why we need to say whether the system is observable or not is very, very important for you to study the control of the system. Okay? Last time, based on this definition, we start deriving something. Let me jump a little bit to the example first. Set up an example so that you have a clear picture of what's going on. I'm going to change this example. To some example, maybe have just a tiny bit of physical relevance so that you can draw a connection with your intuition. Okay, so that's my purpose. Example, my favorite example that I use quite a bit is point mass example. I have a card, even in this square, right? I use this. Okay, it's a mass, and I have my control is the force applied to your card. Is a point mass. You can think about that as point mass. And this is, let's call it a P. Okay, position. This P is different from the state dimension or output dimension P. I assume that's clear from the context here. This is position. Okay, so the dynamics equation is just Newton's second law. Okay, it's m p double dot equal to u. That's it. Let's say we don't have friction. Let's assume we don't have friction. If you have friction, you minus some friction function. Let's say this is my dynamics. Then I can do state variables, right? We can define, let's say x1 equal to p, x2 equal to p dot. Makes sense, right? That's how we introduce state. All right, then we have a state space model. Will be x dot equal to what? X dot equals to 0, 1, x, okay, 0, 0, x plus 1, 0, u. All right, so that's my dynamics. Oh, u over m. 1 over m here. Okay? Typically, I choose m to be constant 1, so everything is clean. But anyway, let's use it. 1 over m. No questions, right? That's the state. That's the dynamics of your system. Okay? I haven't say what's the output of my system yet. By defining this, I'm not defining the whole system yet. So this system is really a mapping from input to output. I have to specify output. Okay. There's two ways of output. Let's call it the one choice. I would say option 1. Option 1, let's say y equal to 1, 0, x. So you measure position. Okay, somehow you have some position measurement to determine the location of position of your cart in your physical world. Okay, then option 2, I would say y equal to 0, 1, x. I can choose to measure velocity. Of course, if you have all the sensors, you can measure all of them. In this case, but in many real-world applications, there are too many states. I don't think you can measure all of them. You can only measure a subset of the state. Okay, that's continuous time model, right? And we learn how to discretize it. Everything out of the analysis based on discrete time is very easy to understand, but the same principle applies to continuous time as well. But let's move to discretization. So that's discrete time. So discretize with, let's say, delta t, sampling time delta t. If we use Euler discretization, that's the only one we learned. It's nothing but xk plus 1 equal to what? Equals to identity plus delta t times a, right? Multiplied by xt plus delta t of b of uk. That's the formula we derived before, right? Relatively simple. In this case, it's nothing but identity is 1, 1. This part is delta t. Delta t times a here has a 1, right? So delta t here is 0. Oh, sorry, 1, the 1. This is xk, and this part is 0, delta t divided by m, and the u of k. Okay, that's my discrete time model. All right, that's my discrete time A. This is my discrete time B. What about C? What about discrete time C? It doesn't change. All right. Discretization only affects the differential equation. Y and x are related not in differential equation form. It's in the static mapping, right? We talk about dynamic versus static quite a bit early in this class so that you know all the kind of subtleties here. So here it will be the same. Option 1 is still 1, 0, xk. Option 2, yk is 0, 1, xk. Okay. Now I can ask you the questions. There's two systems with two different outputs, by the way, okay? Is this observable? So can you get all the states you need to design your controller or evolve your system? Observable? That's the question. I think even the simplest, just this one, it's hard for you to see exactly whether the system is observable or not, whether you can use input-output to truly know, uniquely determine your state trajectory or not. I think this guy is observable. We will see that later, okay? And this guy is not. If you measure just the velocity, the system is unobservable. That's, I think you may, if you do robotics, you have this IMU, right? You use IMU to measure the velocity and accelerations of your robot, okay? And if you don't have some kind of external measurement to correct you, you will have drifting over time. There's no way to counteract that drifting if you don't add additional measurement because the system is unobservable. Because your system is unobservable in this case, okay? That appears quite a lot real world. We will see that after we drive the observability condition and to see whether this is tell us the answer. So let's have this question in mind, and then go back to see how we can use the system model to analyze the conditions to derive the conditions to ensure observability. Now it's clear a little bit, right? All you need is to know, I want to know my state. For some reason, I just really like my state. I have to know it. And if you don't directly measure it, can I use multiple steps, input, output, to guess or uniquely determine my state vectors? Okay, that's all it cares about for observability. And last time we derived, we want to use input, output to measure, right? So we just list input, this is output vector, and how do they relate to the state, especially initial state versus, and also the input. And somehow we end up here with a big output measurement sequence, right? And a big input sequence. These are known. All these are known. The only unknown in this equation is small x0. Okay, the only unknown here is the small x0. Actually, you have more equations than the unknowns. Okay, now in the shorthand notation, the reason we start introducing this big capital Y and U is all because that make our life much easier. So you have YK equal to OK X0 TK UK. This guy is something unknown we want to solve, or we want to determine, or you want to estimate, either way is fine, okay? So then if I move all the knowns to the left or right, whatever, to one side, and OK X0 should equal to this. This guy is known, okay? This is known. At any given time, you know this vector. And the question is that, can you use this vector to uniquely determine X0? That's the question. Okay, I want you to think, what are the conditions can ensure this guy can be uniquely determined? If the system, there's no noise, let's say there's no noise, then there must be a solution. Okay, that thing is governed not because of the math, it's because of the physics behind our assumption. Okay, so if your state and the output is generated truly by this model, then of course there must be a solution. Now the question is that, can you find the unique solution? Okay, so you know exactly what's going on. All right. So case, if you want to solve anything like this, if you want to find unique solution, what's the condition you need?
The columns of OK, the linearly independent.
So that means the columns of OK has to be linearly independent. Okay, all the columns are linearly independent. In other words, the null space, that's our review lecture, okay, the null space of OK has to be trivial, only contain 0, okay? If not, let me just briefly recall, I think you should have learned this, known this before. So for example, suppose OK X0 equal to B. Suppose I find, and there must be a solution, okay? Suppose I can find one. This is one solution, right? Suppose that means X0, let's call this B, okay? B is the whatever on the right hand side. For any, let's call it X tilde, belong to the null space of OK. By definition, that means what? By definition, that means OK times X tilde has to be 0. Any vector in the null space, it has to be 0. Okay, OK times it has to be 0. All right, then I can say OK. I know, sorry, that's not QK. OK times X0 plus X tilde also equal to B. Right? So whenever this executor is non-zero, I already find another solution that satisfies this equation, right? So executor has to be 0. Okay, null space has to be trivial. Otherwise, there's infinite many solutions. Whatever in the null space can create another solution for OK times x0 equal to b. Okay, so x0 can be uniquely determined if the null space of OK is trivial, that only contains 0. Null space is a subspace, it always contains origin. Okay, in other words, rank of OK has to be n. Whether you can go through those steps, huh?
OK has n columns.
Yeah, OK has n columns. OK has n, you can see this OK, right? OK dimension is, let's mark its dimension. What's the dimension? It's k times p by n. K minus 1, this is k equal to 0 is c, ca. You have k copies of c dimensions. Its dimension is p, as we assume the output dimension is p. So you have k p cross n. It's really a tall and thin matrix. Okay, the rank has to be n. It's just like what Yuntian said, it's all the columns has to be independent. That's the same as rank equal to n. Okay, I still want you to recall our key lemma or fact, conservation of dimensionality. I'm not sure whether you still remember it. So dimension of null space of OK plus the rank of OK equal to number of columns of OK. So this is number of columns. I think in homeworks, in lectures, we somehow discuss this and use this fact quite a bit to derive or analyze null space of any matrix. Okay. What do we have got so far? If you want to uniquely determine initial state, somehow there's a matrix OK. That OK matrix has to be full column rank. The rank of that matrix has to be n. Okay, but that matrix is somehow changed over K. Depending on how many measurements you use, the rank of OK can be different. Okay, it's like you have more information coming in. Can you use the more information? It seems like it's more possible to give you more information about x0. Okay, let's say that this is already our observability condition, but we need to simplify that later so that it doesn't depend on K. K is arbitrary. Anything finite is fine. All right. One remark here is that input U does not affect ability to determine x0 because it's only a fact here. It's some part of the things will be subtracted out, so you don't need to worry about U. So it doesn't matter. The only thing matter for observability is OK. So C and the CA. So sometimes, maybe most of the time, when we say something observable, a system, we wouldn't say A, B, C, D. Sometimes just AC is observable. It's just like the case of AB is controllable. Same thing. AC is observable means the B and the D are irrelevant. Okay. Now let's summarize or simplify the condition with us again using Kelly-Hamilton theorem. It's the same thing as before. For controllability, we design a controllability matrix, right? If you still remember this M, C, controllability matrix B, A, B, A squared B. That thing need to be full rank. Okay, rank is N. Now for observability, what we care is what? OK, right? This is OK. C, CA, all the way to CA K minus 1. I can keep increasing this K, right? And the observability test is, in essence, in spirit, is the same as controllability test. In the sense that adding more K's, if K goes above or beyond N, it doesn't really add any more information. Okay, if it is not observable after K equal to N, then there's no hope for you to make it observable when K is N plus 1 or N plus 2. You see what I mean? If I go back to this example, of course, when K equal to just 1, you just have one measurement. Of course, you cannot uniquely determine, right? You have two unknowns, one equation. Of course, you wouldn't be able to have a unique solution, all right? But if you add more, you may have more chance. You have two equations. You have 3 equations, 4 equations, 5 equations. Actually, only 2 equations is enough for you to determine whether it's possible. Adding more will not be useful later on because of Cayley-Hamilton theorem as well. Let me briefly argue, because we argue this in more details for the controllability. Okay, so here, MO defined in terms of N. N is the state dimension, right? N is the state, A is the state dimension. So we define MO. I don't care about K bigger than N. Okay, I only define up to N. If I check MO, if MO rank is N, then I'm done. If MO rank is not N, I'm also done. I don't need to do N plus 1 and plus 2. Okay, so that's the only information this test is trying to tell you. AEC observable, any X0 can be uniquely determined by these guys. According to what time is it? Okay. According to the previous slide, okay, X0 can be uniquely determined if what? From previous slides, if the rank of OK is N for some finite K. You're with me, right? That's what we discussed. By the fact or theorem, the Cayley-Hamilton theorem, I would just say CH theorem, if you don't mind. CH theorem. On slide 3, is that 3? Cayley-Hamilton theorem, where is it? Non-trivial fact 12, okay? On slide 12. Sorry. On slide 12, Cayley-Hamilton theorem. I would directly say that now, okay? Rank of CA all the way to CA K minus 1. Okay, that's K you can pick arbitrarily, okay? As long as finite. Equals to rank of CA all the way to CA N minus 1 for K bigger or equal to N. Exactly the same claim, almost the same claim as the controllability test case, right? In other words, Of course, for k equal to n is the same, doesn't matter. These two are the same matrix, so you don't need to worry. For k equal to n plus 1, so that means I'm just say, I don't want to argue that again because we argued that already for the controllability case. So I would say rank, if you want to say rank C all the way to CA n minus 1 equal to the rank C all the way to CA n minus 1 and CAN. Okay? You can continue this. Keep adding more. You're adding several more rows, P of P rows in this matrix. All of them are linear combination of previous rows because of Cayley-Hamilton theorem. Okay, because A raised to the power n is a linear combination of identity A and up to A n minus 1. So adding more, it just doesn't matter anymore. Okay, there's this final deadline for K, which is n. If you don't make it up to n steps, sorry, you cannot do it. Okay, because the nature of your system. All right, any questions? I'm going to skip the proof or for this. I will say, and then system observable equivalent to rank of observability matrix equal to n. All right, so that's good enough. Now let's look back of our simple example. Let me add one more page. In this case, let's use our observability test to see which one is observable. In these two cases, you still remember, right? One choice is you measure the position. The other choice is you measure the velocity, speed, okay? So which one is observable? It's hard for you to see, but let's say for case 1, I have MO. What is MO? C and CA, because n equal to 2, right? So you only need CA. That's it. If you cannot make it by CA, there's no way you can do it in CA plus 1. So then let's say this guy is C is 1, 0. What about CA? C times A. C is this times A is say that again. 1, right? This is a 1. This one is delta T. Okay? So this rank of this MO is 2. All right? Rank of MO is 2, so it's observable. The second state is observable. Now for case 2, what is MO? Still C and CA, right? But in this case, C is different. C is 0, 1. This C times A, what is it? This is 0, 1. Huh. You cannot determine the initial state. In other words, which one you cannot determine? The position. The position has ambiguity. There's no way you can uniquely determine that, right? So this is a rank. Rank of MO here is 1, unobservable. Observable. Okay, it's similar to your gyro or MU. You cannot, if you only measure the velocity, let's say, or acceleration, let's say just the angular velocity, then the angle definitely will have drift, okay, over time. But that difference may be big or small, that's fine. But in theory, you cannot uniquely try to have more rows. Okay? This guy means in 2 steps. I mean, in 1 step, this first case also cannot uniquely determine x0, right? But in 2 steps, he can. But in this guy, in 2 steps, he cannot. But let's say, okay, let's say k equal to more, right? C, CA, CA squared. Let's add 1 more row. That will be 0, 0, 1. That's the first one, right? Then you need to multiply this guy times A again, but then that will be also 0, 1. All right, you find out after here, everything is 0, 1. There's hopeless. Okay, adding more input doesn't help you. At least doesn't help to have more measurement. Okay, the number of measurement you need is just n steps. Any questions? No questions. This is the most abstract lecture, I think, in this class. It's not hard, it's just a little bit abstract. You don't have too many connections to, it's solvability, right? The things we learned before, I think you like, things has numbers, things has physical meanings, that's better, right? But this is like when you can easily solve solutions without knowing whether under what conditions you can solve or the solvability of the problem, right? If I gave you a linear equation, x1 plus x2 equal to 3, x3 plus x4 equal to 5, you can solve it when you were young, maybe even in elementary school, right? But what we are talking about is under what condition those kind of linear equations have solution. So that solvability issue, that's what you need to learn, okay? For as a undergraduate student, not a elementary student, okay? All right. Now let's talk about, so the only thing we learned so far is that solution, how to derive state space models, and how to check system stability or not. We talk about internal and external stability, I assume, okay? Now I can test you even BIBO stability because we added some information on that. And also controllability, observability. When I ask you those concepts, you should tell me the definitions, not the test. Definitions are from different from the test. Okay. Another very important thing, maybe it's worth discussing several lectures, but I'm just going to give you a short coverage on that because if you want to say you have taken state space or modern controls without knowing those concepts, and also the next one I'm going to talk about, you are not qualified. Okay, that's the important thing you have to know. It's called Similarity Transformation of your system. As I mentioned, all these models are wrong. Okay, there are some representation of the physical world. When you develop your model, you can choose different coordinate systems. Do you see what I mean? You can choose different coordinate systems. And choosing different coordinate systems should not affect the key properties of your system. Okay, so that's all it means. And this can be easily defined or argued through by the similarity transformation matrix. Let's briefly mention that. First of all, I think in the first lecture of linear algebra review, I already talked about the somehow basis for vector space and what does it mean, right? Let me briefly cover that again or a little bit. Whenever I say a vector is 2 and 3, what, okay, there's a vector, the two numbers, I put them together. Other than that, I'm asking you what's the vector or physical word meaning of these two. And in essence, or fundamentally speaking, what are the coordinates? Vector is a physical quantity. There is a vector, let's say my pen, this, if you think there's an arrow here, this is a vector, okay? This vector uniquely exists in the physical world, in the universe, located in Shenzhen, in SUSTech, in this classroom, in my hand here, okay? If I want to tell you there's a vector here, I have to somehow create a reference system. I have to say, what are my coordinate basis vectors? 2 and 3 just means there's a vector x, okay? 2 and 3 means this is a physical vector, okay, on my piece of paper here. 2 and 3 means I have a coordinate. This guy is my E1. This guy is my E2, okay? I use these two basis vector to represent the sum, the linear combination of this basis vector, like to express this physical quantity. So this essentially means this is 2 times E1 plus 3 times E2. Okay? 2 and 3 always means 2 times the first basis vector plus 3 times the second basis vector is my vector. I assume that's, I briefly covered that, but I want to remind you about this. So numbers is not just a number, it's really have physical meanings. Okay, but the same vector I dropped here, right? So this is my same vector x. I can change to other coordinates, right? I can use different basis vectors. Suppose I have a basis vector, let's say, for example, we can choose new basis vectors in R2. Suppose my first basis vector is 1, 1, second basis vector is -1, 0. Whenever I write these coordinates, I somehow implicitly assumed I use some coordinate system to represent this new basis vector already, okay? There's a loop of reasoning, but I assume you know what I'm talking about. So in other words, this guy is almost like this. This is my P, okay? -1, 0. So this is my P2, okay? Roughly, all right? So I can say this is my new basis vector. In the new basis vector, I also want to express x. But you can easily find out based on those numbers. So this x actually equal to 2, 3. That means if I say this is 2E1 plus 3E2, okay? But that's also equal to 3P1 plus P2. If you can, you just multiply this, I think 3P1 is 3, 3, plus P2 minus is 2, 1, 3, okay? In other words, I can use matrix vector. So this is the linear combination of vectors, right? Linear combination is always matrix vector multiplication. That will be P1, P2 times 3, 1. Okay, 3P1 plus 1P2. Linear combination of these two vectors. This is my new coordinate of x with respect to the basis P1 and P2 if I have two new basis vectors. Okay? I assume you know this already. If you don't, I think today is also a good a good recall for you to pay attention to. Okay, I think we should take a break. All right. Let's go back to the class. Okay. As I mentioned before, you can choose arbitrary coordinate system or basis vector to represent vector, so that your system, the dynamical system, is just vectors, right? A vector, how the vector update. If you change your coordinate system, your dynamical system also change. The representation or numerical value of your dynamic system will be different, okay? But hopefully the property doesn't change. After we went over those basic concepts, I hope when you see this, I say I did a change of variable. Let's say x equal to p and z. I introduce a new variable z. And here p is invertible. It's a non-singular, I'll call it non-singular matrix, okay? Non-singular means square and invertible. Non-singular matrix. Suppose P is non-singular matrix. When you see this change of a variable, the relation between x and z, they're related by x equal to p times z. You should think of z as a representation of x in a new coordinate where the columns of p are the basis vectors. Okay, so let's go back to our example P1 and P2, right? So that essentially means E1 and E2, that's identity, by the way. This is identity matrix, right? Times x1, x2 equal to P1, P2 times z1, z2, okay? Both x and z are coordinates. Whenever you say coordinates, you always say it with respect to some basis vectors, okay? When you don't mention the basis vector, canonical basis vectors that everyone knows. Okay, so this, when you see this relation, you will say, oh, okay, z is the new coordinate under change of coordinate system. And the basis vector for z is the columns of p. Okay, that's enough. So before our system, let's say, is evolved according to a x vector, okay, xk plus 1, axk, buk, and yk equal to cxk, duk. Now I want to change my representation. I want to change my coordinate system. So I say I define a new variable z relate to x equal to p times z, all right? That's if p is invertible, then you can calculate z from p inverse x. Okay. Now I want to say how the system what's the system ABCD matrix in the new coordinate system, in the new coordinates z. You can derive it, right? So zk plus 1, what is it? It's p inverse xk plus 1, right? If you want to derive your system dynamics using z, then your dynamics involve z. You cannot say sometime involve x, sometime involve z, okay? You only have one state vector, which is z now. Okay, so you want to relate z at k plus 1 with z at time k. So that will be p inverse. This is what? axk plus p inverse b of uk. You're with me? Conceptually, I think it's hard for you to stay understand, but whenever I derive something arithmetically, I think everyone is easy to follow. P inverse A, this guy is what? Xk equal to P times Zk, right? So I have to derive the entire state update equation using Z only. Okay, P inverse B of UK. Okay, so then I somehow regard this guy is my A hat, right? P inverse AP will be my new A. This guy is my B hat. Now yk is the output, right? Output is a cxk plus duk. Cxk is p times zk plus d times uk. And this one will be my c hat, and the d hat is the same. Okay, so now I have my new ABCD matrix, so that it's hard for you to tell where to come from. If you don't know x before, if I give you a state equation, zk plus 1, a hat, this, then it's a standalone state of the equation, right? If I tell you this equation is from the same system, physical system, but under change of coordinate, then you know how they related, and the relation is given by this a hat, b hat, c, d hat. Okay, so this ABCD of this form are called equivalent system. So I have ABCD defined as above. It's called equivalent. ABCD defined, let me write it down maybe. Let's call it A hat equal to P inverse AP, B hat equal to P inverse B, C hat equal to C and P, D hat equal to D. This defines a relation between ABCD and ABCD hat. Okay? Defined in this one, defined ABCD hat defined in one for any non-singular P. I didn't say with P. As long as non-singular, the derivation works, right? For any non-singular P, if I define this ABCD and this ABCD hat are called equivalent. They are the same representation of the system under different coordinate system. You can think this way. Okay. All right, so as you can imagine, the physical property, whether a system is stable, whether it's controllable, whether it's observable, those fundamental properties shouldn't change if you change your coordinate system, right? It will be a disaster if you choose a coordinate system because everyone will have different coordinate systems, right? The system behavior changes. That will be a disaster. So this is just trying to kind of assure you that this won't change. But you can easily argue through the definitions of those properties. For example, I would say A is asymptotic stable if and only if A hat is asymptotic stable. Can you roughly see why is the case? Because that's the general case. We went through the general case last time, right? Let's use general case. A is T inverse, where J is the Jordan form. Okay? If diagonalizable, then Jordan form is diagonal with eigenvalues on the diagonals. Okay. But A hat would be what? P inverse. So that would be P T J T inverse P inverse. Okay. That will be PT times J times PT inverse. If you take inverse, you need to put the second term before the first term, right? So that's exactly this. So A is similar to A tilde, I will call A hat, sorry. A hat is similarity transformation similar to A and has the same set of eigenvalues. Okay, so they also have the same eigenvalues by this property. So because eigenvalues need to stay inside unit circle, so these two are equivalent in terms of stability. All right. The others are similar, but a little bit, I think it's easier. So let's look at one more, okay? Controllability. Are you done with this slide? This is Jordan form. The most general case, okay? For controllability, all we need to test is the controllability matrix. Okay, so let's say, suppose, let's see how the two controllability matrix relate. So M C hat equal to B hat, the new matrix, right? So it's B hat, A hat, B hat, and all the way to A n minus 1 B hat. That's fine, right? That's our controllability matrix. You want to test whether this is full rank or not. But if you just plug in the B hat, A hat formulas, you will see this is P inverse B. A is P inverse A P, right? And times B hat is P inverse B. Okay, all the way to A is P inverse A. Sorry, A hat is P inverse A. So this is a P inverse AP raised to the power of n minus 1 times B hat, which is P inverse B. These two terms canceled out. So hopefully, okay, if you multiply multiple times the same thing, so you will find out this is P inverse times B AB all the way to A raised to the power n minus 1B. So it's P inverse times MC. The fact, or maybe I will ask you to verify yourself, my favorite three letters. It's rank if P is non-singular. Rank of MC equal to rank of P inverse MC. The controllability only cares about the rank of MC, whether it's in or not, right? If P is full rank, these two has to be the same. You should be able to argue this based on whatever you already in algebra course studied before, or based on the review we did before. Either way is fine. If you need help on this, we can discuss offline. Okay. Similarly, this has the same relation like that. Okay. So this, if you just write it out, you can find that MO hat equal to MO times P. Okay. And these two are also, so I'll say rank of MO hat equal to N, if and only if rank of MO equal to N. Okay, so this guy is MO times P.